research network, plus all of the guys from the Wigner Research Center, and I especially thanks to Gergely to organize this, and Ferenc and Máté and Gábor who are running the wheel and will make this 2 days a successful story. So that's it. Enjoy your stay and enjoy the workshop.
Thank you very much, Peter. So this may be somebody to shut me down at a certain point. Okay, so now I hope we are online and we have everything ready to go. So just as usual, a quick presentation on the GPU laboratory. Maybe we can shut down the lights. If not, then go back, Balázs, please. Okay, it's coming back. So anyway, here you see the usual first slide, and let me again thanks the support by the Lombik Limited, the Streamage VC and the Statcom, and of course the NRDO office of Hungary. Please share it. So for the Lombik sense, the most important support from them to have these videos in a nicely cutted version and edited version and uploaded. So for example, the last year presentations are already available on the previous year slides. So if you can go there, you can see all slides and you can use in an educational material for later use. Can we go to my presentation, please? Maybe at least I need the presentation. So in the the next slide on my presentation, you can see the main topics of this series, which is very much the same as we had last year. So the classical and quantum massively parallel computing, which is very much connected to our GPU laboratory, because we have many running projects, and the topic, some of the topics will be dedicated to the classical, which is mostly by Gábor and my part of the group, and the quantum computing simulations, which are not real quantum computing at the moment, but quantum computing simulations on FPGA type of machines. This is the talks which are dedicated to this on tomorrow morning by Zoltán Szingolai. Okay, so the topics are here, but we have now a new direction. So we have also connection to the industrial partners and other institute, and this is what why we have the subtitle that not only the scientific but the applied part of the things. So if we would go to my third slide, which is just highlighting the logos of the supporters. And finally, I would like to say a few words for the new form. Some of you who are already connected with us, that we used to have the GPU Day, the Wigner GPU Day, which is connected to the Wigner GPU laboratory, which last year went through a little bit of change, because we joined together with the Wigner Analysis Facility, a large scale computing, classical normal computing to attached with the Sam Alice experiment. And we also have the CMS and Alice experiment collaboration tier 2 sites at the Wigner Institute. So these all together joined and formed the Wigner Scientific Computing Laboratory, which we applied and won the possibility to participate in the top 50 Hungarian Research Institute of the NRDO office, which is a very unique and special title which we could got, and finally, can I go to my slides? Okay, so this was what I was looking at. Oh, okay, and this is the program. But anyway, so this is the VSC lab, and this was the point when last December, 17th of December, we received this title by the NRD office. Then just very shortly, 2 months later, we got a special visit by István Szabó and then their colleagues to see that what we really have as a hardware. And the very interesting thing that of course we were in a lucky situation since we are doing this for a long time and the structure is very much liked by the NRD office. So the original aim is to promote and help with massive parallel computing for scientific and non-scientific applications. So this was the original idea of the GPU days since the very beginning. So some of you know the history. So the original idea was to deal with GPU calculation, and this is why we inherited this nice name, the GPU. However, we are much more beyond this dedicated topic. So in 2009, with Mate, who is now in the industrial part, but we started only with 2 GPU cards, and later on we got newer and newer versions of the different machines. And then at the time, the high energy physics and the gravity was the main research direction. Later, we extended this to the institute-wide, so the Wigner Institute, anybody could join, even some other institutes, the Astronomy Institute, the Kunkoy Observatory, people started to use their machine as well. And just very shortly in 2010, we figured out to make this event the GPU Day, which started at that time, and today we are in the 12th in the series. So it's a long-range thing, and we are very happy that we're having this, and we are very happy that, for example, one of our main supporters, the Lombic Limited, is still with us on this more than decade. Okay, so then things has been changed, and as you see now today, we are as a Wigner Scientific Computing Laboratory having a much more bigger thing. So the change haven't, so the original aims and the ideas haven't changed, but now we have the nice group. Balázs is unfortunately on the other continent in this time, but Balázs Szigeti is trying to help us, Gábor Bíró also, and Majoros Balázs, who are together with us and help if you have any questions during the conference. Okay, just see that how our impact is on the field. So here you see the typical numbers. The first is the academic, the second is the industrial, and the third part is always the student. So we are usually having about 100 people in person or online, and this is also true for the certainties what we have today. We're slightly below, but we will see. And as an outcome, we have industrial academic partners, scientific publications, and these fellowships during the last 12 years, we were about 40. Okay, so last year we got a big investment from the Wigner and the Eötvös Loránd research network. So it's about 150 million forints went to refresh the systems. So we bought new GPU machines. We started again this fellowship program with a little bit of support, and we also had the upgrade of the VLCG Tier 2 sites and the ALICE analysis facilities. So now we have new and fast machines. Even just 2 weeks ago arrived this Maxceler FPGA for the quantum computing simulations. So how does it look like? This is the place. This is room 2, which is dedicated to the laboratory. You see the 6 rows, what we have now. Each row is about 17 racks. And this part is the analyzing facility. And this part is for the VLCG Tier 2 site. And this part now today is the Wigner GPU laboratory. And we have some extra smaller size connections also here. So it looks few, but of course, you know, the GPUs are very powerful and we have limited things in the racks. This is how it looks like now. Very recent machines, we have this NVIDIA Tesla T4, the NVIDIA A2, and the strongest one is this NVIDIA 800, 8 times in a super micro server. And what is coming is a new gate server for us and some meeting then switch connecting all the things together. Here you see the structure of your computers, and this is what you can see over on the web page. So if you need certain dedicated resources, you can go on the gpu.vigner.hu and you can see all the available resources what you can use and apply for. A few words about the analysis facility. So this is a very special dedicated site for the CERN computing. So it's a nice joint thing to have a specific type of activity analyzing data, and we have the freedom to set a hardware in large scale in order to satisfy the high bandwidth and the typical needs of such a site. So it's very unique. So we have this playground, which is very unique. Even CERN has no such an opportunity to build up a structure and play with it in a certain case. So this is why it's so important. So we have a raw capacity of this like 2.6 petabyte, which of course in RAID it's 1.3, and we have 124 worker nodes with 32 virtual CPUs for each node. And since this is how we started, so that was the plan, and then we could get the first machines in 2 years ago. And then today we have 9 of these racks. You see that basically it's almost, apart from one, this is copy paste of each other. And we could find a new way of solution to find the border between the Vigner data center where we are located in order to work together with them and to find out what we have to do, what they have to do. It's of course, I mean, we are working together, but there are credits and specialties which are, we have to split at a certain point, and this is where we split these things. And then you see also the VRCG T2 site, where we have about 2 petabyte capacity, full capacity with 3,000 virtual CPU cores, and we also have a new site, this virtual site with 1 petabyte of this. These are new and ongoing things. So the very new thing that in high energy physics so far, the single core analysis used to run on this system, but together with Alice, we invented the 8 core machines. And you see that starting from 2001 Q1, we are running even single and multi-core jobs, which is very unique and much more efficient what we used to have in the system. And so far, more than 165,000 jobs, sorry, 1,635,000 jobs has been done on this system in machines. And here you see the single core and multi-core usage. And we also have a publication together with the Alice collaboration, which presents all of this data at a certain point. This is again some points. And I think maybe just I would like to show that during the last 12 years, these are the connected academic and non-academic institutes and collected on this nice slide. And just one word on the future. So we have, of course, since we are now a very big, how would I say, laboratory, so we have to make long-range plans. So the short time scale, we try to finish the running projects, what we have so far. And of course, we are just closing and opening in the second semester the new VRC Lab grants for young scientists. So this is what has been done in the first semester of the year. And of course, we would like to, after COVID, restart these lectures on modern computing in science series. So this is exactly some of you who joined last year GPU Day, it was in November because of COVID and many other issues, but now we are trying to put back to this the Q2, and then the other event, which is more educational part, will goes to the original place around Q3 to Q4 of the year. Okay, so at the intermediate time scale, we would like to increase the bandwidth between the laboratory and the world, which today is today is 10 gigabit, but it's planned to go up to 100, which is really needed by the ALICE and CMS collaborations, and of course, hopefully by GPUs as well. And the very long range plan is just few days appeared in the internet that there will be a new supercomputer, HPC supercomputing in Hungary. It's called Levente. I don't want to say anything on this because our colleagues from HIFU will speak about this soon, a few words. So I think that's all. I do not know how much time I use because my chairman disappeared. But no, I'm taking care of the time in the future. And let me call the second speaker, who is Zoltán Lehoczky from the Lombik Limited. And the talk will be accelerating massively parallel .NET code using FPGAs with Hash layer. And in this project, we are very much connected to the Reddit Wigner and the Lombik company. I give you this one.
All right. Okay. This is a lot of sound. Please stand by while we load your GPU Day experience. Just a second. Could we stop screen sharing here? Because then I will take over. I will do a live demo, so hence the loading time. And let me share my screen, so you should also be able to see it. And it's on, great. So, yeah, it's probably too much. Okay, now it's perfect. All right, welcome back. One, two. Okay. I'm getting some mixed messages here, mixed instructions. All right, is it all right? Okay, then welcome again, everyone. It's good to be here again, just as last year and the year before, and actually there on the very first GPU Day. And it's great that this now is the the natural time for the GPU Day just before summer really starts. Now, as announced, this event is both for academia and industry. Well, now I'm from the industry, so forgive me if I'm not necessarily scientific enough. What I would like to show you today is one of our R&D projects that pretty much turns software into hardware implementations, and what we would like to collaborate with you, researchers. So let's get into it. I'm from a company called Lombik Technologies. We have heard Lombik being mentioned here a couple of times by Gergely. Thank you. We are day-to-day web development company, actually, with .NET. We use an open source content management system called Orchard, and we mostly have clients from the US and Western Europe who we work with as Orchard specialists. Companies like Microsoft or governmental institutions like the Smithsonian Institution. But when we are not doing our day-to-day stuff, then we are doing some research and development, out of which one of the projects is Heslier. Heslier stems from actually before the company, and we have talked about it here at GPUSA many times, but it's a little bit different every time, so it won't be a repeat. But let's first talk about you. And for those beautiful people on the other side of the internet, let's suppose that you are doing some number crunching. And by number crunching, I mean, well, something in the fields of AI, machine learning. Of course, it's also widely used in scientific research as well. Or you are working with data which is in some kind of image form. I'm talking about image in the wider sense, not necessarily pictures, but also something like radar images or any matrix-like data. Or you are doing something with fast Fourier transforms. Or you are doing something with Monte Carlo simulations, these classes of algorithms, or something with data compression, which of course is widely used in Alice as well. Now, what can you do to make it faster? Because let's suppose it runs for 1 minute, but you are running it every 5 minutes, so it's too slow, or it runs for 1 week, and you want to run it every month, so it's also too slow. Well, of course, you can take your codes and make it faster just by modifying the code. This process is what we call profiling and optimization. Let's suppose that you have already done that. We have also heard that there are 8 core jobs at the computer center. Of course, that's also an approach that you can parallelize your computations. Instead of single core, let's suppose that you have already done this as well. And finally, you can use more hardware or faster hardware naturally. Those are all the basic stuff. Let's suppose that you have already done that. And of course, we are at GPUSA, so the next step is heterogeneous computing. Now, let's talk about that part a bit more. We have already heard FPGAs being mentioned. I would like to use FPGAs in this project. Now, I suppose most of you are familiar with FPGAs, but if not, FPGAs or field programmable gate arrays are pretty much chips that can be reconfigured to behave like any other chip. This being a simplification, of course. But this is hardware development. You pretty much need hardware development knowledge for it. Now, why would we use FPGAs? I'm not talking about why hardware engineers use that and why it's used in chip manufacturing and stuff like that, but why would you use it as an accelerator, as a compute accelerator, like GPUs? First of all, FPGAs have some edge in parallelism. So, of course, CPUs can be parallel. And I would say that CPUs, the chart in blue, are on the lower end of parallelism here, even with 3264 for CPUs or stuff like that. GPUs, the bar in the bar in green, are on the higher ends here because you have thousands of processing cores. But FPGAs are kind of in between, with the level of parallelism in the order of hundreds if we are talking about something like something akin to CPU cores. Now, talking about program complexity, so what you can run on these devices. CPUs win here, you can run anything. GPUs are on the other end, I would say, because the programming model is much more limited there. And FPGAs are, again, kind of in between. Although you are not really running a program on an FPGA, of course. But where FPGAs really shine is power efficiency. So how much stuff you can compute with 1 watt of power. Now, when we are talking about mobile devices, that's of course a paramount aspect. But even when we are talking about high performance computing, that matters a lot, of course, for power consumption and also to dissipate that heat somewhere else. cooling. And FPGAs are really, really power efficient. The reason being is that with an FPGA, you are pretty much creating a processor architecture for your application. It just computes what you need to be computed, nothing else. And because of that, it can do a lot of stuff, a lot of computations with one clock cycle with 1 watt of power. The downside being, though, is that it's hard to use them. It's easy to program a CPU. It's nowadays relatively easy to program a GPU, but it's quite hard to develop for an FPGA. You are not writing a program for an FPGA. You are creating a hardware design that will be implemented on an FPGA, and because of that, it's super low level. You know, you are thinking in terms of clock cycles and wires and gates, not the problem or the algorithm that you want to solve. But with Heslier, the units is non-scientific. It's complexity. But with Heslier, we intend to bring that complexity down to the software development level. But to put the joke aside a bit, we maximize for, let's say, development productivity per performance. So if you want maximum performance, probably what we intend to do with Heslier is not for you. But if you want better performance than with CPUs, for specific algorithms, better performance than with GPUs, and you don't want to learn it for months and take the development for months, then such high-level approaches are the way to go. Okay, so if Heslier is such a magical stuff, then what is it actually? Well, it's not magic, and it's not a silver bullet, but what it is a tool that takes a computer program and creates an equivalent FPGA logic out of it. And not just any computer program, actually, but .NET. Has anyone worked with .NET here before? Yes, a couple of people. Even Gergely, great. Now, for those of you who don't know .NET or haven't worked with .NET, .NET is a programming platform, a framework that supports a lot of programming languages. Probably even if you haven't worked with .NET, you have worked with C++ or Python or JavaScript. Now, these are all languages that you can run on top of .NET. And it has to be processed now. But if you haven't worked with .NET, why would you use it, even for scientific computations? Because the .NET of the old is about enterprise programs. And 10 years ago, if you have heard .NET, you probably thought, okay, a line of business applications, enterprise resource planning, something like that, but nothing about science, nothing about high performance computations. Well, the .NET of today is quite different. In the last 5 to 8 years, it has been through dramatic shifts, also with a focus on performance. It's a modern programming environment, cutting edge all the way. Don't I have 40 minutes? Okay. It is a huge development community. Millions of people work with it, and it's open source. That wasn't the case before either. We at Lombic are a very open source company as well. It's quite important for us. A lot of open source projects. Open source matters, and .NET is open source. So in the end, what we intend to have is the benefits of FPGA computing for every one of us. You can get a performance increase if your algorithm is compute bound, so CPU bound, or memory bound, because FPGAs also have a very efficient memory model. And you get higher power efficiency, and at the same time, it's still programming as usual. So let me show you how it actually works. And I've brought an FPGA board here. this is not the high performance computing FPGAs, but this is an embedded FPGA, an FPGA that is widely used in embedded systems called a Zynq. It's used in robots, drones, and on board of satellites. And that's actually the next use case we intend to utilize it. But it's easy to demo. For high performance computing scenarios or anything where you need a lot of juice, it would rather be something from the cloud, something what one of the FPGA manufacturers, Xilinx, calls data center accelerator cards. So let me log in to this little FPGA. It's actually not just an FPGA, but it also has as sorry about that. But it also has an ARM CPU core. This is a little system on chip with a CPU that's on the same chip as an FPGA. And that's good because you can run a full Linux on it. That's what I connected to with a shell. And we can also compare the performance. So let me run a demo. And what happens now is that we are running a highly parallelized little sample application. I will show you the code in a minute. First, it starts. First, Hessier starts generating the hardware, which I will also show you. It's pretty much generating hardware code. And once that's done, it will execute the whole thing on as software on the CPU part, on the 2-core ARM chip that we have. And after that, it will also execute it 3 times on the FPGA. So we can have a comparison. Now, let's take a look. The first thing was the software execution, which we see the results of here. It took about 25 seconds. All right, so that's our baseline. Now let's see how much the whole thing took on the hardware. So when we execute it on the FPGA. And here we have one of the measurements. It took around 240 milliseconds. So a lot faster. But the 240 milliseconds is actually just the time spent on the chip. If you also take the communication round trip with the CPU into account, then it's a bit more. But that's just the first time penalty. When we run it the 2 other times, when all the caches for the communication, not the execution, for the communication are warm, then it brings down to almost 240 milliseconds. All right, so that's probably worth considering this performance increase 100 times. Now let's see what I actually used for this sample. What I used is not a real-world application. It's just a small sample of the kinds of algorithms that are especially suited to be accelerated with Hessier. It's called parallel algorithm, and well, it's, you may have guessed it, a highly parallelized algorithm. What it does, again, is just a sample. What it does is that it starts this many 260, in .NET world we call them tasks, but you can think of them as threads. Pretty much we start 260 threads. But we are not oversaturating the CPU, even if it doesn't have 260 cores, which CPUs rarely have. Because the .NET task scheduler will take care of just starting as many threads as there's capacity on the chip. So we'll use the maximum performance of the CPU. And well, what are we doing with that performance? This. Again, just a sample of that simulates that you are doing some compute bound computations. It's pretty much just some conditional logic that's executed 10 billion times. And then we wait for all of these threads to finish. And finally, the output of all of these threads will be the output of our algorithm. Again, not a real world example, but an exaggerated, massively parallelized sample. Up on GitHub in the SDK that I will show you the link to, we have a couple more samples, including Monte Carlo simulations, including some image processing stuff. So, all right, so we have seen how it works in action, and well, what does it run on? What's this little thing I have here? This is it. This is a development board by Transelectro. It, as I said, contains a system on chip called Zinc, Xilinx Zinc, a 7030 family one. It's an ARM CPU, a dual-core ARM CPU packaged together with an FPGA. And actually, the chip itself is that little thing in the middle. I also have a daughter board here, a daughter board and a motherboard that connect together. So actually, the whole the system on chip and the corresponding board is much smaller than what I have shown you here. And this is why this is a system that's also put on board of CubeSats. It's small. I mean, the physical form factor is small, and the power consumption can be quite small as well. In nanosatellites, new space nanosatellites, this is widely used. Of course, not exactly this, but the space-ready version of this board. And okay, where does the magic actually happen? What does Heslier generate? Do we have any hardware engineers here? I've seen one in the back row there. But anybody has written any VHDL or Verilog, or probably high-level hardware designs with LabVIEW or something like that? Nobody. Then this is your first time seeing under the hood. This is where all the magic happens. This is VHDL. This looks like code. It is code, but it's not a program. It's a hardware description. This will be kind of compiled into a hardware implementation, and this is then something that we can load onto the FPGA. If you are creating a physical chip, something like this will be used as well. But the point here is that this is what's generated by Heslier. Again, something you can check out in detail on GitHub if you are really inclined to check out 1,000 lines of generated code. But the more important thing here is that if you scroll down, we also see something called parallel algorithm. So that's familiar, right? We have seen that in C# too. Now, of course, the reason is that, well, this is where we have the implementation for our parallel algorithm. And this stuff that we have here has the index 0. And if we scroll down, then it has the index 1 and then 2. Now, probably you know where this is going. If you scroll down even more, remember we had 260 threads, right? So if we scroll down a bit more, we see the same stuff with the index 247, and then even more, we see again the same stuff with 259. These, by the way, are just type declarations, not the whole code. The logic is a bit down, but it's really long. I don't want to scroll down and dump it on you. But here we have 260 copies of our algorithm. That's where the parallelism comes from. So we started 260 threads. On a dual-core CPU, just 2 threads will be used. 2 physical threads will be used. The CPU won't be oversaturated because .NET takes care of that. So we will have a queue. But on an FPGA, we can actually execute all those 260 threads in parallel. We have a hardware level parallelism that matches the parallelism that our algorithm needs, because we kind of created a processor for our algorithm. That's the whole point of using FPGAs as hardware accelerators, and we can do this automatically here. All right. So that's how the whole stuff works. What else do we have there? I mentioned data center accelerator cards by the manufacturer Xilinx. we have support for Xilinx's Vitis development environment, which means that we have more or less support for every modern Xilinx FPGA out there. Also high performance data center accelerator cards, the kind of stuff that you would use in something like the Wigner data center, and also for boards that are used in embedded systems like this Zinc-based board that I have shown you here. It's also possible to run the whole thing on premises. As you can see, I plugged it into my laptop. You can also buy a card, plug it into your PCI Express slot in your machine, or it's also available in the cloud, so you can just rent virtual machines with these devices. I will be curious whether we have the same cards in the Wigner DC. And these ports, as I mentioned, are widely used in the aerospace industry as well as another application. How faster is it? Does it make sense to use it? Now, of course, again, these are benchmarks. Real world applications depend on real world scenarios. But just to give you an idea, these are the numbers that we have measured on the data center accelerator cards, the high-perf cards. The details and how we measure these and the exact methodology are detailed under that link that I have there. But in image processing tasks, it was about 30 times faster than the high-performance CPU that were available in the virtual machine. For other applications like this parallelogram that I've shown you here, there was about a four times acceleration. Perhaps the reason for this is because these cards, the Alveo cards, are very memory efficient. They have some high-performance memory on board, very quick to use from the hardware fabric. So for image processing, of course, you need memory too. On the Zincs, so what I have here, we have slightly different numbers. Image processing was less pronounced, but still a lot faster, an order of magnitude faster than CPU. And for the other samples, we have 2 orders of magnitude faster. And similar comparisons for the power efficiency too. For aerospace applications, probably the power efficiency is actually what matters more, rather than the raw performance. You know, their power, of course, is scarce. You'll have to dissipate that power, which in vacuum is kind of hard. As we are talking about optimizing for 0.1 watts. And something that's interesting for scientific computing, and something that we learned about from Wigner actually a while ago, is the posit number formats. You know, floating point computations use or may use a variety of number formats, but probably what you have already utilized before are the IEEE number formats that have been with us for 30 years or 40 now probably. But there are new number formats. One of them, which promises to have better accuracy and better range with the same amount of bits, is called POSITs. It was created by a mathematician called Dr. John Gustafson. But we also created a .NET library for that. The point here is that you can also take custom floating point number formats or custom number formats in general, implement it, and with a high-level tool like Cassier, you can get a hardware implementation pretty much in minutes. And the missing piece of the puzzle is, of course, you, because while I'm here, why I'm here is to have a discussion with you, get into collaborations where you can do something useful and something cool in the world of science. Now, high-performance computing, of course, is used in a wide variety of scientific computational tasks. Our approach is a bit different, a bit experimental. So we are also looking for partners to conduct such experiments. If you have some thesis work going on where you are writing some completely new code, then probably using such experimental tools is something that that you can do, or that you can also involve in your thesis work. If you have some existing codes that you want to rewrite, you want to optimize for heterogeneous computing, then one approach that you can take is utilizing FPGAs. Again, this is not a silver bullet, of course, and it's not a substitute for GPUs. Both are needed, both are useful, both have their different advantages. Or if you have some applications in the aerospace space, then especially because nowadays you pretty much have to use heterogeneous computing approaches to squeeze out all the last computing power from your available electrical power. So that was it pretty much. If you liked it, and I really hope you did, then here's the link to the SDK up on GitHub. There are all the samples, all the measurement details, all the benchmarks as I mentioned, and all the information for you how to get started. But if you like to get started, please just get in touch with me on these contact details, because I would be happy to help you. And be ready, because I think FPGA computing will be a lot more important in the future than it is today. Although it is a lot more important today than it was on the first GPU day. So thank you very much.
Thank you. Thank you, Zoltan. I think the last sentence was very much true, that it became much more important, the FPGA-based technology, since the first GPU day, especially thanks to the possibility to using the .NET and Haskell joint code to make things easier. Questions from the audience?
Just want to ask, what are the testing? Okay. I just want to ask, if you have a complex algorithm or something that's parallelized, what are the odds that, okay, maybe you get VHDL, but what are the odds of that VHDL actually synthesizing? Because there's a lot of stuff going on with the Xilinx compiler to actually get into the fabric and get a physical realization. So do you have any kind of knowledge on benchmarking this for very complicated algorithms, maybe that are heavy on things like multiplication, multiplexing, things that are not so trivial?
Thank you for the question. The trick here is that Haskell supports a limited subset of .NET. Of course, not everything makes sense. So if you can write something that's Haskell compatible, and Haskell won't tell you that, hey, this won't work, change your code, then it will be syntactically correct. Now, one thing where it might not synthesize is if the design is too complex. Indeed, we don't have any help built into Haskell to help you with determining that yet. Unfortunately, you have to try. Pretty much, the approach that we take here, it's a preliminary approach, is that take one of the samples that looks quite similar to the algorithm that you want to implement, try it on that device of yours, see how much resources it takes, and then take an educated guess of the level of parallelism you can put into your algorithm, try it out. If it fits, great. If not, reuse it. Unfortunately, we don't have anything better than that. The good thing is that with the current hardware compilers, the synthesizers, Vitis, you get an approximation of the resource usage pretty early on. So at least that feedback loop of trying to fit the design is relatively short.
Okay. Further questions? Zoltan, please.
Thanks. I'm just wondering what the difference were between the two cards that you showed. The performance was greatly different. Mm-hmm. So was it in the second one more gates, or what was the reason why you had more performance?
Yes, thank you for the question. The two cards are widely different. And what probably wasn't entirely clear is that what we compared them with, the CPU execution, was also different. So on this board, we compare it with the onboard ARM. For the data center accelerator card, we compared it with high performance server CPU on that machine. Now, the main difference here is that there are fewer gates, yes, logic units or logic gate, no, something I'm thinking about the Xilinx terminology, whatever. There are fewer resources on this embedded board, yes. I think at least 20 times fewer resources of every kind. Secondly, the architecture is quite different as well. The point of these things is that you get a hardware accelerator, like a hardware accelerator core in your CPU. So it doesn't have its own RAM. If the embedded memory resources it has are also limited. Versus on the Alvo card, which showed very nice numbers for image processing, there's high bandwidth memory embedded, pretty much there in the fabric, and a lot more distributed RAM as well. So that's more meant as an external discrete accelerator that you offload computations to in a more batch-like work, versus with the Xings, it's like having a CPU core.
Further questions from the audience? Please.
Thank you. I would just like to compare, ask you how the evolution of the FPGAs compared to GPUs are. The GPUs tend to double the performance of the GPUs. How does it parallel with that?
Great question, and I don't have an answer for that. But I know that the size of gates, the nanometer, but can't remember the name of what we call it, just in Hungarian. Anyway, the size of the gates shrinks at least a generation later than for CPUs. But otherwise, it's pretty much in lockstep, especially that now both big CPU manufacturers, both their FPGA manufacturer. Intel bought Altera, which was the second FPGA manufacturer, and AMD recently bought Xilinx, which was the first. Other than that, sorry, I can't recall any specifics about the evolution, but they are improving continuously, of course.
We are lucky because we have a professional in this. Just let me make an advertisement that we at the Wigner in the Data Acquisition System Laboratory are creating such a cards, building up such a cards. So Werner is one of the professionals who are designing and programming these things. You can say a few words regarding the evolution of FPGA chips and cards and the resources. The small Xing FPGA is about 20,000 other gates cells. Like the high-end Alveo cards is about 2 or 3 million flip-flops and logical gates. Is 100 times more. And one of the reason that we have a better FPGA price, because when a new technology comes out, then mostly the manufacturers try to build with as many gates and logic as silicon, and making the FPGA is like a test for the new technology. So as the CPU technology, GPU technology evolves, we have a better FPGA cards, and nowadays we have a interest from accelerator community. I don't know if it's also mentioned that in cloud-based centers like Amazon and Azure from Microsoft also have this kind of plan, so you can run this Hessler generated code in the cloud. So with each year or generation, we have more and more resources in the FPGA is one of the reason or the promise of this high-level tools like Hessler that we have a more control over the complexity, that we can describe the problem in high-level language, and we get the low-level VHDL, which we can compile with the vendor-provided tools. And yes. Okay, thank you very much. So the time is over. So let's thank Zoltan again.
Thank you.
And, let me call the next speaker, who is one of the founder of the Wigner GPU Laboratory, Máté Magyegri, who will speak about OpenCL ecosystem updates on behalf of the Stream HPC company.
So, welcome everyone. My name is Máté Magyegri, and I have been working at Stream HPC for 2.5 years now, roughly, but it's almost 3 years. And for the past year, I had the luxury of working on open source projects entirely, mostly around the OpenCL ecosystem, which I would like to present some of the things which we took part in this past year. And the topics are around the OpenCL SDK and the OpenCL layers, and some actual news around the OpenCL ecosystem. So what is the first party OpenCL SDK? Just a quick recap if somebody hasn't been reading the news around OpenCL. I would say recently, but OpenCL 3.0, if I'm not mistaken, it's nearly a year old, or more than a year old now. It is the reimagination of OpenCL as it is. So the last, I would say, widely supported standard or version of OpenCL was 1.2. After that, it picked up a lot of cool functionality, which not every vendor really agreed on wanting to ship inside their runtimes, primarily because some of, like each and every vendor had like one specific feature that they were to some extent allergic to, and like that feature didn't perform well on their hardware. So 1.2 is the last feature which every vendor agreed upon, that yes, that has the core feature set which performs well and makes sense for their hardware. And so OpenCL 3.0 is a reboot to the entire ecosystem, and they took it is actually source compatible with 1.2. So if somebody has a working 1.2 application, just recompile it works. And actually, recompilation is needed. And everything else after that is an extension, which one has to query, like whether it is present on their implementation or not that they are running on. So it adopts the Vulkan methodology, like have a slim core profile and everything else is extensions, which is massively popular in Vulkan land, this approach. So this slide is from my last year's presentation. And back last year, I knew that there was a lot of goodness coming in this domain, but most of them I couldn't talk about either because it wasn't public or because it wasn't ready yet, wasn't shipping. But 1 year has passed and now everything can be downloaded from online. So what I mentioned last year, that the OpenCL SDK, which aims to be like the one-stop shop for every OpenCL developer to get productive programming OpenCL, we're coming to GitHub near you. The link is actually live and it points to the OpenCL SDK on GitHub. And it has a lot of, it has everything that we've been working on in related to the SDK. So what is inside the SDK? So some of these components were already present on GitHub. The SDK is just, to some extent, like a super project containing all the things that that is required to put together a development environment. So, for example, the headers, which everybody needs to get the OpenCL API entry points, the types. And recently, there are 2 new headers which help in creating your own implementation of OpenCL. So if somebody wants to do that, and somebody has some custom silicon that they want to light up using OpenCL, it's fairly popular to pick OpenCL because it's simple and people have, so the expertise is readily available. If somebody has some in-house silicon and they want programmers, they want to recruit programmers, then OpenCL is a good choice because easy to learn and there's also expertise available to leverage. And also if somebody wants to create their own layer, there's also a utility header for that. The OpenCL ICD loader, if somebody wouldn't know, it is the library which you link to when you're developing an OpenCL application. It isn't the library implementing OpenCL, so it's just orchestrating the function calls and it relays every function call to the particular implementation that the user intends it to. It's dynamically loading libraries under the hood. It is the very first function one would call the CL get platform IDEs. Under the hood, that is when the ICD works its magic and looks for DLLs on the system, query the Windows registry if somebody's on Windows, stuff like that, to load the actual implementations and present them to the user in an easily consumable manner. This is the part which is gravely missing from OpenGL, for example, where all the implementation is inside OpenGL.dll, and Vulkan has similar functionality built in as well. And the C++ header. So if somebody isn't very fond of writing the more verbose C API or using the more verbose C API, then they can use the canonical C++ bindings to the API. It does reduce the verbosity and it also adds some safety guards around adding or setting kernel arguments on kernels. There is some minimal type checking there, and it greatly helps with the reference counting of API objects through RAII, if somebody knows that C++ idiom. And something which wasn't present inside the SDK previously or in the ecosystem, there are now inside the SDK some utility libraries which take off some of the burden of the programmer. So there are some common tasks which are associated with developing OpenCL applications. And these are now given to the user as like one-liner functions. And it just it improves the overall developer experience. And if somebody has some utility that they think like, hey, this was extremely useful in my applications, and this is like a common pattern, and everybody has their own set of utility libraries when they develop applications. So if somebody thinks that there is a particular feature that they have a solution for and they want to submit it as a utility function or type, then open a pull request on GitHub. It's freely available. The contributions are welcome. And some of the things also inside the SDK are SDK samples. So this is a simple n-body calculation. And it should be in a loop. I don't know why it is running. So there is some graphics interrupt samples as well. That n-body. This is Conway's Game of Life, which is a nightmare to video encoder. So this is almost like white noise. That's why it's really hard to see on display. So some of the typical graphical samples have samples for as well. This is this demonstrates the pattern of calculating something in a texture and then just splitting that texture onto the screen to see like what's the contents of it. That is something which is fairly common. And the other one, n-body, is like a 3-dimensional sample. It's just a point cloud in 3D. And if this was an interactive sample running, I could like pause it and then turn the camera around and inspect any part of the space that is being simulated. And then there are the classic console examples as well, but they are less flashy on slides. And we wrote documentation for everything inside the SDK, the utility libraries, the samples, what particular features they demonstrate, what's the API surface that's being used. So if somebody is looking for the usage of some function, like how is this function used in the samples, they can also search for that. And we've also invested in getting improving the CMake support as well, which was kind of lagging previously. So some parts of the documentation are part of the OpenCL guide. It is a separate repo on GitHub, and it supports like overview kind of documents on what is OpenCL, how to use, what is offline compilation versus online compilation. So the OpenCL SDK has a lot of cross-referencing to the OpenCL guide, where things such as like the getting started guide, how to get started programming OpenCL on Linux and Windows, there is good documentation there that one can consult. And the CMake support is also extensively documented there, what the current state is and where we are planning to go with it. And also as a part of Stream's engagement with OpenCL, we've invested in improving the platform support and compiler support of the headers and the loader and the samples as well. So we were aiming for getting all 3 major platforms, or 3 major desktop platforms, Windows, Linux, and Mac, being most widely used compilers, MSVC, GCC, Clang, and crank up the warning levels as high as reasonably possible and get everything to compile warning free, because OpenCL is a infrastructure library to some extent, so it is fairly low at the dependency chain if somebody depends on OpenCL, and we really didn't want for warnings to bubble up from the bottom of the stack, which like plagues everyone's console output. There is also not just CI but CD in place. So the OpenCL SDK has automated binary and source releases on GitHub. So whenever we tag a version, there are regular quarterly releases to both the OpenCL standard. So there are quarterly like bug fixes, occasion extensions being added, and when there are new samples showing some of those off, and there are required header updates or loader updates needed to light up the new extensions, then everything is released immediately in the OpenCL SDK. Then onto OpenCL layers, like what they are and what they help us with. So again, going back to that last year slide, when I mentioned last year that there is a new ICD functionality layers, then this like the next slides are detailing what I thought under the hood, what I thought meant by that. So borrowing the image, or like rehashing an image, borrowing it from Brice Vidot, who's the original author of this new ICD functionality. If somebody has programmed Vulkan previously, then this may be or this idea may be familiar to you. So without, when like the old school, or like without layers in place, or layers being used, if there is a user application and it's calling some OpenCL functions, then there is the ICD loader sitting in between the application and the implementations, the drivers. So the ICD term I have used previously, and apologies if I didn't expand on it, is the installable client driver. The ICD is the implementation, or one implementation of OpenCL. So the vendors like Intel, AMD, NVIDIA, they ship a DLL which has the implementation of OpenCL for their specific hardware in it. And the ICD loader, what it does is that when the user invokes, creates, so the user interrogates the ICD loader, what platforms are available, and when they get a handle to a platform and they start creating objects like context, devices, buffers, events, whatever, using that platform, then the ICD loader sets up pointers, and it relays the function calls to the appropriate drivers. And what layers do is that sitting in between the ICD loader and the actual implementations, there is a stack, and apologies, those ICD loaders should be layer 1 and layer 2. Yes, that is copy paste error. It's fixed on a later slide, but I failed to fix it. So there are multiple layers sitting in between, and we can see, I tried to convey the information using colored arrows. Like if there is, for example, if we look at the green arrow from the application going into function 1, then there are 2 layers active in this application at the moment, and only one of them handles that particular function, like it has some extra feature lighting up in that layer, and the ICD loader immediately relays that call to the layer that handles it. And if there is a function which is handled by both layers, then the function call will traverse through both of them. And then similarly, the return value will backpropagate, if I may use that term. The return value will go back the same arrow, and every layer will have the chance to observe the return value coming from that function. And they can do whatever they want with it. Most likely, they will just observe it and just pass it on to the stack. But any functionality can be inserted there. So this is like, and this magic is done through a dispatch table, which the ICD loader sets up, and it gives to each and every one of the layers. And if you're interested in how, in more detail, how this feature works, then I would highly advise watching last year's IWOCL International Workshop on OpenCL. Brice Vidot's talk, who gave a nearly 2-hour presentation on like how this feature is implemented under the hood and how you can author your own layers if you want to. So this is what layers are. And then what can you do with layers? So one of the things, but just about everything you can do with layers. But one of the things which we were engaged with is creating an object lifetime tracking layer for OpenCL. So if somebody has written OpenCL applications using the C API, then like towards the end of the application, some similar pattern is quite common when like the programmer releases every single API object which they acquired from the runtime. This isn't strictly necessary, like if you're leaking API objects at the very end the application, then yes, the runtime and the operating system will clean up after you anyway. It's just like if you didn't, so if it's just like leaking ordinary memory. Although it can be the source of bugs, and it's very important to take care of this if in a normal and shipping application. But just by looking at this, it may not be immediately visible. Like, did I forget to release something? And if I did, like, I wouldn't be able to tell. My application would terminate normally, and nobody would tell me that, hey, by the way, there's that 1 or 2 objects that you've leaked. And one of the things which was initially implemented by Brisvido, we just added a few features on top, is the object lifetime tracking, which does signal the user at the end of main. One can register like functions to be invoked by the C runtime after main has ended. And there we actually print to the user like, hey, by the way, there were 2 objects that you forgot to release. And one is lucky if it's only 2 objects. Like a bit more, this is still one of the things which is easiest to screw up. And I have fallen victim to it one too many times, but I also see that my university students get this wrong. So this is an easy pitfall. Like, here is a quite common loop which calls some kernel on some queue in like a million times, right? We don't know how long steps is. And we want to collect the net kernel execution. So the net time the device has spent calculating that kernel. So we associate an event with the running kernel. There's no error handling, so please, just so that we can fit on the slide. But we query the profile command start and profile command end. It gives back a nanoseconds of some device timer, and then we just add the difference to the total time. And what have we forgotten to do here? If somebody guessed that releasing the event, yes, that is what we have forgotten. So here we just create an event handle by just declaring it. And event creation is one of the things which is most implicit in OpenCL. So there is no like CL create event. There is one like CL create user event. That's kind of a different beast. But for events tracking API activity, they are created by just adding a pointer to that handle to the specific API. And this is like the enqueue range kernel. There is the address of event at the very end, and that is what creates the event for us. So it's really easy to forget to release that event because like we didn't really write a code like CL create event. And since we have this in a loop, if this loop executes a million times, then well, best case scenario, it's just a memory leak because the underlying runtime, the OpenCL runtime, will just create new and new events for us, and there will have the runtime will have a million events to keep track of. A slightly worse case scenario is the application will crash. So an OpenCL runtime will say like, yeah, you have 100,000 events and you surely did not mean to create that much. So like, I just crashed because like, I don't want to take care of that much events. It's too slow. So these are some of the scenarios where like an object leak detection layer can come in handy, so that the layer will tell you, by the way, you have 1,000 events that you forgot to free. And then one can start hunting like, okay, then where am I leaking events in my code? Object lifetime layer can also help with things such as double releasing a resource. Some APIs will return an error if you do that. And that's the correct thing to do. Like if somebody is double releasing, sometimes the application may just crash if somebody is double releasing an event that is like a less that's less convenient way to signal a user that the code has some error in it. And if there is like 100 lines in between, then it's not almost evident that, hey, by the way, I already released this resource a few hundred lines up. And this is something which the layer can also help with, and the layer can, in fact, short circuit the call stack and not call into the ICD. So as I said, that when the application calls into a function and the ICD relays that to the stack of layers, the layer has the an option to not call into the underlying ICD. And this is a feature which we've implemented because we've seen that some runtimes actually crash on double freeing a resource. And that's not good developer experience. So there is an option to tell the layer, like if the layer can already say that this object is dead and you have already released it, then do not call into the ICD because it may take down the application. And there is, yep. And this is like double freeing is akin to use after free, like releasing is kind of using an object. And it can be that somebody accidentally already released an object and then tries to query some information from it. And again, some runtimes for performance reasons do not really validate that the objects which the user provides are really alive, they are well behaving, yada, yada, yada. And they just return the devices that were associated with the context. Like they still keep the context alive. They didn't really free up memory tracking that object. So on some runtimes, this code actually executes and doesn't even return an error. And that's a bad thing because that's not portable code. And also, this is one of the reasons why using dangling references is possible. So if one looks at this code, we create a context A, we release it, we create context B, and then on the second release, we will actually be releasing context B because the runtime does have the option to recycle pointers. So ultimately, context A is just a pointer to some driver implementation. It's the pointer to implementation idiom, all handle pointers. So this code will do what the programmer intended to do, but it's really dangerous because it does rely on the runtime recycling pointers just for performance reasons. And this last feature is something which we do not have in place yet. It requires the ICD to insert a dictionary in between the application and the ICD and always translate and make sure that every pointer is unique, which the user gets and nothing is recycled, so that we can issue a diagnostic on such uses. And another layer which we've implemented, this one we've done from scratch, is input argument validation. So there are quite a lot of entry points to OpenCL. In fact, there are 124 core API functions and then 109 extension functions which users may invoke. And each and every function has a set of preconditions and postconditions. And those are only documented in the API reference guide. So the HTML or PDF or whatever rendering of the API you have. And going through that guide or that PDF, and then whenever somebody is writing a language projection or some binding to the API, may that be C, C++, C#, Python, or whatever, most often these APIs want to issue an error on their own terms. So in C, it would be an error code. In the C++ bindings, it can be an error code. There can also be a C++ exception. C# would typically, C# bindings would signal errors as C# exceptions. And we don't want to do that for every single language we have there. And there are more language bindings to OpenCL, by the way, not just these ones. So we do not want to duplicate that work. Somebody have to go through the standard and read 233 functions worth of preconditions, postconditions. So this is like one API, the CL enqueue write buffer. It has this is where the input arguments are documented, what they must be, like an offset pointer, shell, sizes in bytes, read or written. Buffers refer to a valid buffer object. So valid buffer object means that it has to be live. And then these are the postconditions to the functions. Like if the user has violated some of these preconditions, then this and that error code will be returned. And this is something which we do not want to do more than minimally sufficient, and that what is minimally required. So our idea was to generate all the checks from the XML and both generate a layer for checking all these preconditions and postconditions. And lucky for us, the OpenCL standard, as it is codified in an XML document, so that is the one source of truth, what a type is and what a function argument is, what its type is. And to take the simplest possible case, like release device only has one argument and the only precondition is that that is a valid object, so it has to be alive. This is how it looks like in the XML file, the definition of this API entry point. And what we did is that we went ahead and we added to the XML some machine parsable definition of the pre and post conditions. We've also added like a default logging message. This is something which could go into a C# exception if the language binding wants some textual representation of what the user violated and why this error is occurring. And so we wrote we went through the spec, read all the pre and post conditions, put them into the XML, and wrote a code generator for it that generates the source code for the C++ layer. So if a new function is introduced, then once it is added to the OpenCL XML, then nothing extra has to be done. The user just runs the code generator again, and then they have an updated layer which takes care of that one extra function. And then in actual news, Sasha Willems, the author of the invaluable tool gpuinfo.org, it's a website which collects the properties of any vendor's some devices. So users can download a client, run it, and then submit the report to this database like, hey, my hardware using this particular driver exposes these features. And this is really useful if people want to check if I want to depend on some extension or some feature, like what kind of support can I gather from the devices out in the wild. And recently, OpenCL was introduced as a supported API, and there are already lots of submissions. But I would encourage everyone to go to openclgpuinfo.org, download the client, and then see like how their hardware fares, what kind of things it supports, and submit a report. Now, oh, this is two-sided. Sorry. So another fairly recent addition to the ecosystem and is work done by Kevin Petit. He's an ARM engineer working on ARM's OpenCL implementation. And he has issued a library, which is a transpiler from SPIR-V to OpenCL-C. So it takes a SPIR-V binary and it emits OpenCL-C code. And the way that looks is like if I have this very minimal OpenCL-C code, it's like as simple as they get. This is SAXP, large vector operation. Then if I compile this code to SPIR-V and then I run it through that library, then the library will emit OpenCL-C code again, and which looks something like this. And if if we look at it, and if somebody has looked at LLVM code previously or has looked at single static assignment type languages, which is like SPIR-V as well, is one such intermediate format, then actually you can, if one would just look, squint and not look at the uint float and just look at the numbered registers and the usages and the operations, it is really just a paraphrasing of the SPIR-V, what is inside. Like there are lots of pointer castings along the way, so everything is stored as a register, and it is pointer casted to the appropriate type when it is being used only. And so, yes, this is what the runtime does, or this library does. And yes, going from a nice OpenCLC code to an ugly OpenCLC code isn't a big feature. Like, this is not why somebody would want to use this library to obfuscate code, although it can be used for that. Its main purpose is to make use of so to be able to use this library. Why are we so interested in transforming SPIR-V to OpenCLC? SPIR-V is an intermediate language. It is the PTX of OpenCL to some extent. It could be called that if somebody is familiar with PTX and the CUDA API. And SPIR-V is widely useful if one wants to teach new languages to OpenCL. So auth kernels in languages other than OpenCLC. And then here is like a short history of what SPIR is. It comes from khronos.org/SPIR. So if somebody wants to look it up, it's also up there. Older versions were based on LLVM. So that was a big pain point for tooling around it. And then enters SPIR-V, which is completely independent of LLVM. But there are bidirectional translators from LLVM to SPIR-V, there and back, both directions. And partly this is what this runtime depends on through Clang. Like if somebody wants to compile using Clang to SPIR-V code. And yes, so SPIR-V is a very useful feature of OpenCL, because then one can gain access to new languages, but it isn't widely supported. So if somebody wants to check whether their runtime supports it, that's the extension CR-Khronos.io program to check if their runtime supports it. And can we actually teach all runtimes to do that, like we using this library? And turns out that yes, like those functions, if we just catch any call to CR-create program with IL, and then what we do is that we actually redirect that call to a different API point. We do the translation inside to OpenCLC, and then we call a different function from the dispatch table, CR-create program with source. Then we can trick the application into thinking that yes, they supported a binary file, but under the hood, the layer will do the transformation, and it will feed it as a source file of an OpenCLC code to the driver. And then the application will think that, yeah, hey, actually my driver just ingested SPIR-V and compiled it. So this is how you would use it in the C++ API, C++ host API. And the reason why it's good is because then one can use C++ as a kernel language. There is a definition of a standard on how to, like it's a version of C++ 17 with some OpenCL specific extensions to it, how to define vector types and stuff like that. And then one can use Lambda functions, templates, whatever they want inside the kernel code. And that makes it much, much easier to author more complicated kernels in OpenCL. And then again, there's an extension for telling the runtime to consume C++ for OpenCL. And then, yes, that is roughly in the actual news and what we worked on OpenCL for the past year. And we're hiring, so if somebody's interested, please see the jobs. Thank you for your attention.
Thank you very much, Mate. Questions from the audience?
Hello. So I was wondering if there's any performance-oriented enhancements in OpenCL 3, because the layers stuff seems somewhat like more of a debugging or development time feature, because it would seem to actually reduce the performance overall, right, to do all these extra checks and whatnot. So I'm wondering if there's anything to enhance the performance, because in my experience, I've seen projects where the hand fine-tuned, to a specific environment assembly code or something could still outperform something done simply with OpenCL.
So yes, those are really two questions together, but yeah, let me try to separate the two. So the OpenCL layers, which I talked about, yes, they are a feature which, if used, then they come at a performance cost, but they are meant for debugging debugging an application. So when somebody is shipping an application, they really should not run code through layers, or they should only run through like a minimal set of layers, which only like add features but not validate. This is the same thing in Vulkan. Like Vulkan has some debugging layers as well, but nobody ships games using these features. So the layers which I talked about, yes, they come at a performance cost, and but one only uses them when they are developing an application. And as for OpenCL 3 API functionality, and yes, and layers are not strictly related to OpenCL 3. So one can use layers on pre-OpenCL 3 runtimes as well. That's an ICB feature. They just happen to come roughly at the same time. And for OpenCL 3, there are various extensions which have been released recently, like in the past year, which do help with performance. Some help with tooling, such as there's a debugging extension in flight, also an extension in flight for querying performance counters on the device. So like measuring time inside the kernel code, which helps improve performance while developing. And floating point atomics was also recently released, which is like a huge performance boost if somebody has to do floating point atomics. But to answer the question whether OpenCL can go under hand-tuned assembly code, but no, it cannot. So if somebody can actually work with assembly code and can optimize it, it is something which we have to do for some number of projects that require like the utmost performance. But experiences that OpenCL C code, or at least my personal experiences, that going under like reasonably good C code is already hard enough. And that remains true for OpenCL C code as well. So I think it's like roughly on the same order of magnitude as optimizing assembly for CPUs. Like to get the last percentages, sometimes even the last 10, 20%, you have to write assembly code. So it's not the last 1% we're talking about. Sometimes it's much more. But OpenCL C or OpenCL 3.0 doesn't really help crossing that barrier, aside from extensions which give you like a baked feature as an intrinsic function that you just call, and it will compile to the most optimal assembly for that specific piece of hardware.
Okay, thank you very much, Mate. So I think we are pretty much in the coffee time. So let's thanks Mate again. Just in the next room to the left for me is the coffee break. We will come back at 11, and please, all the speakers from this next session, you can come and check your talks and upload your talks within the coffee break. Thank you.
Köszönöm szépen.
Okay, let's continue with the second half of the morning session. Let me introduce Adam Pinter from the Wigner Data Center, who is the IT leader. And during the, even as COVID started, we got a very good collaboration together online and in real between the VSC lab and the Wigner Data Center. So please.
Thank you, Gergely. And welcome everyone for this session. I would like to start my presentation with the vGPU concept and how we integrated this into the cloud, and how we can manage these resources for research projects. And I wish and I hope that what I see today and tomorrow is some of the projects can come to this cloud and use these resources. Okay. The IAKH cloud is created by two institutes in Hungary. One is Wigner Research Center for Physics, and the other one is the Stucky. So two sites, two data centers are making this project together. We started in 2016, and as the years went and we got the new ideas and new requests, we integrated this into the new hardware requirements, and we bought new hardware. And what you will see today and in this presentation is the latest technology and the latest capacities. So this cloud is for research institutes, universities, and industrial parts where the researchers can, the research can be done. So those industrial parts. This project is supported by the IAKH Secretariat, and we started officially on 15th of February this year. This is the new capacity. I would like to show you only the most important things, and one thing is new in this cloud, that you have SSD storage, which is which was requested many times, and now we have this capacity with 12 servers together, and the vCPU capacity together is almost 7,000 vCPU. Yes, memory is 32 terabytes of RAM. The SSD storage is 337 and almost 1 petabyte, more than 1 petabyte of HDD storage, which is both of them are HDD and SSD is replicated. The internal network of these clouds are 100 gigabit per sec to provide fast and reliable network. And what is interesting is that we have 72 GPU cards together. On the Stucky side, we have the NVIDIA V100 card with 32 gigabytes of RAM, and in the Wigner side, we have 32 of 800. The GPU memory altogether is 2,500. I would like to show you a rack concept, which is at our data center. It consists of three almost identical racks, but since we have 4 GPU servers, it's a little bit different. And what we see, and visible to see, that the storage we tried to put equally. So if one rack is down, still you have 2 other racks if anything is happening, and the data is replicated based on the rack. So if one rack is down, still for sure you have 2 copies from the data. Each compute chassis, which you see this light green color, consists of 4 nodes. In the next slide, I will show you the exact content. But first, let me show you the A100 card. For sure, you know a little bit about this one, so I won't go into the detail. But you can see the data. This is the 40 gigabytes of RAM version, and PCI Express. We have some specialties in our data center, is that the CPU nodes are from AMD, and this was a new concept before Intel. We switched because then one compute node can have 128 vCPUs, and this was that time was very promising, and the projects also start to use it, and this way it's possible to use bigger and bigger flavors that the virtual machines are using. So, for example, you can have 32 vCPUs or 64 vCPUs per virtual machine. Each compute node have half terabytes of RAM, and the GPU hypervisors have especially a little bit bigger CPU, so to handle the communication between CPU and GPU. For the storage, we use the Ceph, available open source, and we operate it. Yes, we have 2 pools, one HDD and one SSD. And what I mentioned before, we have this rack-based application. There is a specialty at Wigner site is the stable library. Some of the projects requesting this to have extra archive from the data. So we provide this based on unique requests. This table contains the available flavors for our cloud. And I would like to show you the last 4. This is the most important. We have Stucky and Wigner is almost the same, but since they have V100, then they have a little bit less, and we have a little bit more of memory, gigabytes of memory. So, for example, the biggest one is 40 gigabytes, and it's called G2 from 2x large. It means that all the capacity of the card is for 1 VM. If you go down, there is this 20. So one can start 2 virtual machines on GPU card, and etc. etc. I would like to talk a little bit about the user support. We define the basic user support. We define the elevated user support. Some of the projects come with extra consulting needs, so we provide them. For example, data science or other complex problems. We use this daily operation for the elevated support, so they can write us by email, by phone. We can have meetings, so the research can continue, and they have the best available software stack. In the cloud services, we wanted to show the people that OpenStack API is very useful, so they can automate the project generation. So the research project, if they join, the time to work with real data, it's coming closer when they requested the project. So it's faster and faster to have the system, the ecosystem, what they need to work really on the research. We have this VPN service, which means this more secure than in the beginning, and we try to improve in this one, so people can use this VPN service and access the cloud anywhere from the world. And the most important thing now is that supporting the vGPU concept, and I want to go into the detail. So since we have 4 GPU hosts and each card each is 32 UP cards, and the GPU flavor is already very popular, so they would like to use most of the resources already. And since it's a cloud, then if the project finishes, other projects can take this resource and continue. In the beginning of the cloud implementations, only pass-through PCI pass-through was possible. So it is really not flexible, and you need to give all the physical hardware to the user. So there is a step, another step in between. Here comes the virtualization, and with this, it's possible that we share the resources securely and efficiently. For this, NVIDIA created this virtual compute server license. You need to buy it, and actually the cloud operator bought it, so users don't need to bother about this one. And it's automatically refreshing and licensing the virtual machines. This is a graph which shows the types, 4 types. We have 5, 10, 20, and 40 gigabytes of RAM. And what you see in the blue is the already allocated quota in the cloud in our part. And it's visible that most of them like to use this 40, and also 20 is very popular. And we have just like half the quota, which is free. And we wanted to make sure that starting projects with small amount of need, they also can test it and use it. That's why we have like 32 5 from the 5 version, but we wanted to provide also big and bigger versions. Let's go into the detail. How it looks like in a configuration. First, what you see is that you need to define the types NVIDIA provided. It's different for different cards. So we use these IDs, and then you need to show and define each PCI Express address and list it. This configuration goes into the hypervisor with automated scripts, and then OpenStack handles it and can create virtual machines and use resources and accept the requests. What is also visible, that one card can only handle one type, which was a really hard realization. So one cannot mix the types of virtual GPUs in one card. So in the next card, you can have different sets. The third card or the fourth card, you can also have different sets, but one card has only one type. That was a big learning fact. And I hope in the future we can solve this and have a conversation with NVIDIA to find out the solution. But since we have 8 cards, it was possible to create this allocation distribution. Software versions. We need to be very, very careful. Currently, we support hypervisors in Ubuntu 20.4, and it needs to completely the same set of drivers for the NVIDIA from the NVIDIA website, and it needs to go to the VM, and it needs to go to the hypervisor. So all of these components must fulfill these requirements. And finally, we have CUDA availabilities 11.4. If you start a virtual machine in the cloud, what you will see at first base with LSPCI is that only just this PCI Express address and 3D controller. That's what you see. After you install the driver, you will see this detailed NVIDIA commands, and you see that it's an A100 card. For the licensing, you need, we decided that each project have a different token. And with this token, just running a script, actually it automatically activates the pool, and automatically they can use this cloud. The installation steps were the following. So after we set up the hypervisors and each driver was in place, we created, for example, a G2.medium flavor in OpenStack command. And we set up that this resource is with GPU. This is very important. Without it, it didn't work. After we create a custom trait that some of the resources have GPU with 5 gigabytes of RAM, and we set this trait into the special UID what was generated. After this one, we also said that the flavor of this G2 medium is attached to the A100 type. And finally, if someone is creating this G2 medium, only the G2 medium and 5 GB of RAM version can be started. If all of the resources are full, then it's going back with an error. So user can see that it's not possible to start. But we have tons of this G2 medium. But for the bigger one, sometimes it happens that it's full and they cannot start more. So they had to wait when the one project ends and the next one is coming. After this, we deploy the configuration and we realized that I mentioned that one GPU type per card is only possible. So we deployed it again. And finally, if you start a VM and install the driver, automatically, there's a guide for this available. Then you can install CUDA and use your software. From the hypervisor side, it looks like this one, that everyone has a special UID, every resource, and then it's connected to one PCI Express address, and NVIDIA card handles this virtual function because it's a virtual function. And in the end, you also attach the type, and these 3 data comes with each virtual machine. This is also another example. So you can see and list it, and from the administrator side, you can see if they started multiple virtual machines on the host. After this was created, we tested the infrastructure with CUDA libraries, CUDA examples, and after we tested a full allocation test, each GPU, each vGPU, each part was full. So I think it was more than 100 virtual machines what was started, and it was tested that each one can have possibility to license. So after that, we could give this to the users. There was a big test also, what happens when the host is down, if the electricity is down or just the network is down for one host. And it turned out it's really easy to get it back, but you need to check the logs and have the proper documentation for it, so operators can reinstate this state where everything is running. What user feels about this one is the virtual machine stops and starts again. Never happened. What can happen? So, and also what happens when NVIDIA license server is down? Then you need 24 hours to fix it. If it's not fixed, then the capabilities are down. So that's how they make sure that people buy the license. But since we bought it, then they don't need to care about this one. So we need to care about this one and make sure that they are running. What is the future holds for us is that we really hope that new applications and new projects are coming with this into the cloud, and we can provide them a great platform and share all the possibilities and all the results with others, so they can learn and everyone can use it better. Also, we use this Slurm workload manager, and I see that GPU jobs are possible, and I hope we can integrate it in the future. Maybe some projects can use it. Also, I hope that multiple GPU and vGPU implementation is coming in the cloud. If it happens, then we will upgrade to the latest version, so one virtual machine can have multiple vGPUs. And I also wanted to show this distributed deep learning training framework. It's called Horovod, which is making sure that if you have a bigger and bigger workload, then it's possible to use multiple virtual machines with GPU. Really, thank you for your attention. And if you have any questions, let me know.
Thank you very much, Adam. Nice overview. So I mean, many of us has developed codes on the GPU laboratory, so maybe that could be a next stage to make it on a larger scale. So questions all time, please.
Yeah, thank you. So, two questions about resources. You showed a chart about resource usage for multiple VM sizes, and roughly the usage is the same, but there's a lot more quota for smaller sizes.
Yeah.
My first question would be, why so much more quota for the smaller sizes if probably the usage is on the other end? And the second is, you also mentioned that sometimes people wait for the higher end fonts to be available, if I understood correctly. Do you think those are actually needed, or people just submit a job for them because they say, whatever, I may need 14 GB?
Let me answer the second question first. So what we experienced that some researchers like to get bigger quota than needed. So we have a deal in the end that, okay, you just need 3 or 4 big GPUs because first you need to test it. So in the end, there is a really realistic quota for the project. Still, it can happen that many projects are coming. For example, I don't expect this in the summertime, but after the summer, it can get better and better, and sometimes what we experienced from 2016, that they come and really request a lot of quota. Then we need to provide a little bit smaller in the beginning, and in the end, what is visible that we need to buy more GPUs. And for the first question, since you can only create one type in the GPU, if you divide 40 by 5, then you have 8 small instances possible. So you can split one GPU card into 8 small. And there are some laboratory projects, but they want to just experience with the CUDA or experience with the GPU. So we need to provide them also possibility. And sometimes if they come 10 or 15 or 20 people, then we want to provide just this infrastructure that they can test it. Later, hopefully, if they like it, we can improve and request more hardware. So for me, it's very important to show also the concept, not just the big calculations. And sometimes if you run it for 1 week, it's still okay. But of course, it's a really hard project. You need to do it next week, then we can provide them the biggest one.
Right, thank you.
Thank you. It seems that you have very nice user support at different layers. Do you have dedicated people to do this? How many do you have? And they are fully dedicated, or half of their time is dedicated to do that?
Yeah, thank you for the question. Actually, it's a challenge to manage because most of the questions, IT engineer questions, not just basic logging questions. So we need to sit together, for example, in the morning and talk about it. And usually there is 1 or 2 people who are handling these requests and organizing meetings. So let me say that 2 people full time. Yeah.
Zoltan, please.
Just wondering, are these GPUs connected together inside the node with NVLink, or you only use PCI Express?
Yes, since in the PCI Express 4 version, they communicate through PCI Express, not from dedicated cables.
Okay.
But because of the GPU, and we skip the virtual GPU, we skip the pass-through, they are separated, like separate universes completely. Mm-hmm. So if someone is writing a code for it, then we need to give the bare metal service. We need to give pass-through, and all of them are configured now as virtual GPUs. So what you request is it can be a next generation where some of the resources are bare metal, and then we can use this sharing. I think in the Stucky side they provided this also for some of the projects because they have this V100, and then they are integrated into the board, so they have this connection not by PC access, but with the other form factor.
Further questions? We still have time. Maybe then I can ask. So does it mean that the cards are interconnected with each other at the back, or this is not?
They are not connected. And actually, we currently, the OpenStack version doesn't even support it. So,
yeah. And another question. So I could see these cards, the 800 cards, are with the 40 or the 80?
40.
40. So
at that time, it was only available.
Yeah, that was the only.
But I see that in the VRC lab we have the 80, but it's not connected into the cloud, so that's very.
That's a separate development. Okay. Any further remarks or comments? If not, let's thanks to the speaker again.
Thank you for your time.
We can get the next speaker, Zoltán Kiss from the KIFU, which is the governmental IT development agency, and he will speak about the present and the future of GPU HPC in Hungary.
Can you hear me now? So the reason why I'm using my own computer, I try to make this a bit interactive. So my goal is to let you even contribute to this talk, which means that I have this Slido thing that allows you to actually, by scanning those QR codes, you can give some answers for the different kinds of questions here. So just please check this QR code. And the first question is here. The QR code is still there. So what are your current ICT infrastructure requirements? What are you needing the most at this time? So we are just creating a word cloud here with the different kinds of ICT parts. You can say that you need like storage the most, CPUs, FPGAs, as mentioned before. Just, yeah, I expected something like this. So feel free to just write, yeah, all kinds of stuff here. Why I just introduce myself. I'm Zoltán Kiss from KIFU, which is the government agency for IT development. So we are responsible for operating ICT infrastructure for the Hungarian academia and research community, and also we are preparing to offer some services for SMEs as well, so industrial users. So we are very open for a kind of collaboration with the industry and SMEs. 2 years ago, we formed a competence center, which actually aims to develop HPC competence and special. So the agency itself focuses the scientific computation and building HPCs, offering this for community for 20 years now. Yeah, obviously GP1. And now we've got the infrastructure, but also the competence center to be built. The competence center is a very important way to get known the users, to let them know what HPC is, knowledge transfer, workshops, lectures, and so on. So if you're interested on any of these, just check out our website at hpc.kifu.com. So hpc.kifu.hu, it's not com, sorry, it's HU. So which will show you the latest workshops, and we will have a user forum, an annual root user forum, or if you invite it, just learn what we're doing, and we'll try to teach our users what's the best way to use HPC in general. So we've got the fundamentals for even the competence center integrated in the European ecosystem and the infrastructure development itself. And we will have like at least 10 different kinds of workshops each year and so on. So let us know if you want to get involved. So I will talk about the infrastructure because that's what I'm basically more aware of, because I'm just directly working on the infrastructure itself. We are developing HPC infrastructure for 21 years now. You can check out the website. The very first HPC, very nice piece of hardware, but still we keep going strong and offering top 500 grade HPCs. So our systems are in the 500 most advanced computing systems in the world. Try to maintain our leadership here and to offer this kinds of advantage for the Hungarian users. So we are developing Commander now, which is this really nice dog breed coming from the Hajdú-Bihar region, and the system itself will be at Debrecen too. And now, just last week, our newest development called Levente had been accepted by EuroHPC, so they are supporting us to build even bigger HPC. Now 20 petaflops, 64 bits of computation. So that would mean more for like AI petaflops and so on. We've got a very green data center at Debrecen, and we are aiming green technologies. So that's why we've chosen Cray to be our next technology. The Cray is actually giving now the very first and the third most powerful computer in the world in top 500 risk. And so we will have the pieces of technology they are actually using here in Hungary, which is very great news, because that even though it's obviously a bit less powerful, you know, in terms of petaflops, but still the same technology and interconnect and storage and so on, very same technology that the most advanced computing centers in Europe are now using. And for example, the perimeter in Argonne, here, the perimeter here will have the very same space like we have, just like 10 times bigger. So one of the main components of GPUs, and that's why we are here, that we are offering at least 4 petaflops of computing power coming from GPUs only. That would mean 200 of A100. That's 40 gigabytes of memory, so that would mean the really large GPU installation in Hungary, but also offering CPU only system for those users who cannot benefit directly from GPU usage. So there will be like more than 20,000 physical cores coming from CPU only installations, and we'll have 9 terabytes big data machines, a shared memory machine, and an AI node with 8 GPU per node. That would mean that we could use a BitLambda link to offer 8 times 40, so like 320 gigabytes of memory coming from the 8 GPU nodes supported by NVLink. That's a huge amount of graphics memory there. You can see this very nice piece of technology, very dense solution, which is very effective to be cooled. And you can check the details also on hpc.kfu.hu. You can check what CPUs are we using and so on. So you can find Commander there and the infrastructure part. If you have any questions about that, let me know. And we also pre-installing the most used scientific softwares there, which are licensed, so you can see those if you can find, like most of them will support GPU, of course. And the software ecosystem also, once they're talking about the competence center and the infrastructure, we also have to talk about the software ecosystem. So we are developing portal, and we are, that's something that we've been offering for our users, but we're developing even more from some kind of application repository inside, which would support containers, because what could go wrong with containers? So yeah, obviously HPC is not something that's, so usually you just need the bare metal there. So you need maximum performance coming from HPC. So that's not typical of something you want to put any kinds of layers on it. But yeah, containers a huge demand, and there are some other kinds of use cases. For example, AI, where users are very used to containers, and this is something we've been offering for quite some time for HPCs too. With the help of Slurm scheduler, you can actually load containers into Slurm scheduler and have this kind of predefined preload containers where users have this very ready to use kind of environments when they can actually load data into, load the customized code into, and get data out of it. And we want to support this through the marketplace feature of our website as well. So there would be that through the websites, you can actually choose the application, upload data, and then support all these kinds of technologies with the Singularity and Kubernetes to actually orchestrate those in HPC environment. And we will dedicate specifically want to do this for our GPU machines, and also offering obviously for other ones, because it's quite capable AI machine regarding this 200 A100 chips as well. And we're also developing something specifically from the industry, where you are using some methods to actually log in through these machines remotely by a web page, like using some kind of web consoles there, and they can actually check out their simulations there and the logs and any kinds of visualizations. So they can actually visualize and interact with this HPC machine, which is really nice and comfortable way to use an HPC in general. So what's everyone is waiting for? So what will be in Levente? Levente is just awarded like last week, and has about 20 petaflops of joint performance coming from all the partitions. So we want to keep basically similar structure, and we want to offer accelerated computing power in it. So that's why I think it's very relevant for this community here, that we still want to dedicate at least like 70% of the computing power coming from accelerated infrastructure. But we want to add even more, and obviously by dedicating something to big data and AI, obviously using this high performance storage subsystem at Commodore, we are using at least 1 petabytes of really fast memory for 2 million IOPS. We would want to at least offer 10 petabytes of memory here with even more IOPS, and you know, we have the archive storage there. We will have also a modular architecture coming from, which we will develop in connection with the German HPC centers. So this would be something that even the software stack would be somehow developed based on this collaboration with the Jülich institution. We already signed a collaboration paper with them, and the hosting of this facility will be at Wigner. So that's why we are obviously collaborating with the Wigner Institute, and one of the future aspects would be the opportunity to actually integrate quantum technologies, quantum computers with HPC. This is something EuroHPC already has efforts that they want to support HPC and quantum computing integration. And this is something we would rely on the National Quantum Laboratory also and collaborate with Wigner on that matter as well. So, but which accelerator should we choose for Levante? That's why it's a very timely question to ask. So if you have any opinion, just let me know. I have 5 minutes. So there is two kinds of usual suspects here. Is the AMD and the NVIDIA here. So both of them are revolutionizing the industry now, as they say, but there's a huge kinds of leap forward with the technology, because they both will integrate the CPU and GPU together somehow, and with their flagship products, they will integrate those chips together. And even NVIDIA is building a completely new chip like called Grace based on ARM. So the landscape is changing very, very much, and you need to very well know which would add the most performance per power and the most performance of different kinds of code. So those will be like something like called super chips, co-integrated CPUs and GPUs there. So what are your opinion? What are you currently using? Which vendor, which technology are you currently using? Let me know by joining and voting at Slido, because as I would suggest, most of you are using NVIDIA GPUs, but it's not that sure that you'll be using those. The most effective would be that to use those in the future, because I believe there's a huge change. 1 minute. Okay. Yes. I really believe in open source technologies also, which would use both of them actually. But the future might be not the same, because you will have to actually learn program how to use ARM as well, and how to use a very integrated manner with Grace Hopper to use ARM with NVIDIA chips. And that would not mean a very similar software stack. Obviously, they will try to do their best to actually integrate those together, to run CUDA to support those together, and so on. But would it be that effective then? And would it be like working out the box? Or would it be somewhat similar situation when AMD has to build a completely new ecosystem and a new software ecosystem, and build users and so on? So I think somehow similar situation, and you have to build for this new technology, new software ecosystem, and have to teach users how to get the best out of your chips. So this is not something I think it's straightforward decision. So thank you very much.
Thank you very much, Zoltan. Really liked you activated the audience. So time for questions, please.
Thank you for the talk. I'm pretty sure that's very difficult to decide which future technology to use. On the other hand, if you think forward in 2-3 years, then I think the major problem are the software. So most of the HPC users are scientific users at this moment, and I think most of the scientific codes will not be rewritten in a year or two or something like that. So I think it's very important. How do you plan to solve this? do you plan to buy half of the old hardware and half of the new?
Yeah, it's a very hard thing for actually for us, the HPC developers, to choose hardware, because they're actually choosing for future, and they actually want to choose a hardware that's it's not existing yet, and obviously the software does not exist as well. So they actually, you have to buy promise. You have to buy the promise from the vendor that they will be 100% supportive and effective and performant and so on. What we would do is obviously to have those benchmark ready, because we want to measure that. So how they would perform, and we have to have a very clever package of benchmarks built into the tender to get the most out of the chips. And then for the real life, you will have to see, because both chips are somewhat changing, so they have to offer compatibility and so forth.
Further questions? Yeah. Please.
The first one is maybe just a comment, continuing this. I don't think we want to be guinea pigs, right? So we should leave the experimentation for bigger nations who have more money to lose. So I would just recommend stick to the tried and tested technology for now. The other one is, maybe I missed, but maybe you deliberately didn't say anything about the deployment date of Commodore. Can we get any next forecast when it's not coming?
Yeah, it's coming before winter, I think. I'm sorry. Yeah, as you all know, I've already talked about Commodore last year, and I said that it will be coming soon. It didn't because chip shortage and so on. So we are expecting it really to come really soon. The hardware would arrive, I think, really before autumn. So that's, I think, the final deadline for that. So like early adopters would seek us to reach out to us to actually want to try the hardware itself, but I think we would go in full production end of this year.
Thank you. Yeah, actually, that's the case. Many of us suffering two things. One, the missing of chips. The other is the preparation process. It slows down. Further questions from the audience? From outside, Gabo? Maybe I would have one more. That several years ago, like in maybe in 18 or 17, we invited the guy from the Intel company, and they were considering the idea of chips, joint Intel CPUs and FPGAs. And the question, I do not know how this project is going now, but have you considered the other side, so not AMD but Intel hybrid formats? Is there any guess or promise for the future in this sense? Maybe for such a level?
I'm sorry that we're not putting the ecosystem into this answers, but we can submit questions to Slido at any time. I'll do my best to answer that. So yeah, Intel is actually building for GPU and CPU integrated ecosystem as well as a third partner. So they are now just released their desktop GPUs. They will release the latest server GPUs this year that would not perform as well as the others. Maybe a few years later, it will be competitive as GPUs, and they will obviously offer same kind of integration that AMD or NVIDIA is doing.
Okay, so thank you very much, Zoltán, and this nice presentation. And let me call the next speaker, who is Zeyou Wang, and he will speak about parallel implementation of multivariate empirical mode decomposition on GPUs. And now with this talk, we are slightly moving on to the GPU programming itself and to the real material which we are excited in.
Hello. You can hear me?
Yeah, I think it's working. So please.
Thanks. Okay. Hello, everyone. I'm Ziyu Wang from the University of Pannonia in West Rim. And Zoltan Juhas is the co-author, also my supervisor. And today I would like to introduce our research work about the parallel implementation of multivariate empirical mode decomposition on GPU. And the content is grouped into 4 parts. First, I will introduce some background about the empirical mode decomposition, the EMD, and also some variants of the EMD, including the multivariate empirical mode decomposition, the MEM. Oops, sorry, the MEMD. And the second part is about the parallel implementation of MEMD. In this part, I will introduce more details about the numerical steps, the parallelization, and also the data layout in the memory. And next is the performance analysis, including the overview and some kernel performance comparison. Finally, is our future work. So for the empirical mode decomposition, it is first proposed by Huang in 1998. It can be used to decompose a nonlinear and non-stationary signal into several intrinsic mode functions. And each RMF contains only one oscillation mode. In another word, the EMD can convert the non-stationary signal into several stationary components. And the original algorithm is not very complicated. First, the maximum and minimum extreme points are detected. And then based on the cubic spline interpolation, we can get the upper and lower envelope. Then the mean envelope of these 2 upper and lower envelopes can be calculated. This process can be regarded one iteration. After several this kind of iteration, we can get one potential RMF. And this process to get this potential RMF is also called sifting. So after several siftings, we can get several RMFs. And the EMD is not perfect. For example, if we get some intermittent noise in the original signal, this will cause a mode mixing problem, which means one RMF contains maybe more than 2 oscillation modes. This is definitely not what we want. But by adding white noise into the original signal, this mode mixing problem can be solved. And this kind of EMD is called ensemble empirical mode decomposition. The EMD is proposed to solve the mode mixing problem. In another case, if we want to analyze some multi-channel signal, the number of RMFs generated from different channels cannot be guaranteed, especially if we want to analyze some phase coherence and some connectivity problem among the channels. So the RMF's alignment will be a problem. And the MEMD is proposed to solve this RMF alignment problem. For the MEMD, the multi-channel signal is regarded as one multivariate signal in a high dimension space. And during the calculation, the multivariate upper, lower, mean envelope are calculated. And also what we get finally is a multivariate RMF.
But this multivariate IMF can be projected back to channels. So in this way, all the channels can get identical number of IMFs, and the problem of the IMF alignment can be solved. If we want to parallelize this process, its numerical steps should be clarified. So next, I will introduce the numerical steps of MEMD. It's more details. First, we need to project the multi-channel input data along the direction vectors. As we know that vector projection is dot product. It's dot product. So in this part, what we need to do is matrix-matrix multiplication. And after we get the projection signal, we need to detect the extreme points on this projection signal, including the maximum and minimum. For the next, we need to find the corresponding multivariate extrema based on the index of the extreme points in the projection signal. And on each dimension of this multivariate extrema, we need to perform the cubic spline interpolation. For example, if we have an input signal with 3 channels like here, we need to perform 6 interpolations to get the interpolation signal. And after the interpolation, we can get the multivariate upper and lower envelope. By calculating the mean value of these 2 matrices, we can get the mean envelope, multivariate mean envelope. But this is only from one direction vector. If we have multi-direction vectors, we need to further calculate the multivariate mean envelope from all the direction vectors. And in the next part, I will introduce more implementation details. First is how we detect the extreme points in the signal. If we want to select all the extreme points in one vector, the naive way is using one thread to read one elements and its neighbors, then compare these elements with its neighbors to judge whether it is extreme points. But you know, loading data from the global memory in GPU is not quite efficient. And another option is load the data from the global memory to shared memory first, and then perform the comparison in the shared memory. But the shared memory can only be shared by the threads in the same block. So it will also cause some unnecessary memory swapping. What we use is a CUDA shuffle operation to detect the extrema. The shuffle operation provides a function for the thread in the same warp to communicate with each other. So with some warp level overlap, we can select all the extreme points in the signal. And also the overhead of this shuffle operation is just 1 clock cycle. So it's very efficient. And now we selected all the extreme points in the signal. Now, actually, it is a sparse vector, but what we want is a compact extreme vector for the future interpolation. In order to solve this, we use a prefix sum. When we detect the extreme points, we also set a flag vector to remember or to identify the position of the extreme points here. And then we will perform the prefix sum on this flag vector. In this way, we can get all the index of the extreme points in the compact vector. And then all the extremes can be put together without any gap. Till now, we have some known points in the signal, like here, like here. Well, actually, this is a known points, and in our case, it's extreme points. The next step is to perform the cubic spline interpolation. The classic numerical method to solve this is Thomas algorithm. And for the parallel implementation, the cyclic reduction and parallel cyclic reduction is also widely used. But in our case, for example, if we have a trivariate extreme points, on theory, we need to perform at least 3 times cubic spline interpolation to solve the tridiagonal system, but the coefficient matrix only depends on the index of the extreme points. So this multivariate extreme points will produce only one tridiagonal system with same coefficient matrix, but multi-right-hand matrix. Fortunately, the QSparse library provides a function to solve this kind of multi-right-hand tridiagonal system. And this operation can eliminate the channel level iteration. Then it's a data layout in the memory. For the input data of MEMD, actually, we have 3 dimensions to play with. First is the channel of the input data, and then it's direction vectors, and also the time itself. The time itself is also a dimension. So we need at least 2 blocks of 2D memory to store the input signal, the multivariate IMF, and the direction vectors. We also need another 2 blocks of 3D memory to store the projected signals and our final result. We did some performance tests for our parallel implementation based on the EEG Lab simple dataset. There are 4 channels in the input data, and the length of the signal is approximately 30K, and we use 64 direction vectors to project the input signal. And finally, what we get is 8 IMFs for definitely for each channel, and the number of iteration during the sifting process is 10. We perform our implementation on 2 different graphics cards. One is a Titan XP, and another one is the RTX 3070. It's a laptop version. As a comparison, on a machine with 9th generation Core i7 CPU, we run the MEMD function in the EMD lab. It's a MATLAB toolbox. So the results show that compared to the CPU version, the Titan graphics card achieved 190x speed up, and the RTX 3070 graphics card achieved about 55x speed up. We also did some kernel performance compared to the literature. Mujahid and Rohaman proposed GPU accelerated MEMD in 2017, and compared to their kernel execution time, our version achieved a very highlight speed up, especially in the peak detection, which means extreme points detection. We achieved about 187x speed up. Also, in the boundary condition, we achieved about 47x speed up. But there are still some limitations in our performance tests. In the future, we will test more datasets, including the 128 channel, the electroencephalogram signals on the different execution parameters, and the effects of some detailed parameter settings on the decomposition result still needs to be further studied. For example, the setting of extrema and tridiagonal matrix boundary conditions, and the setting of sifting stop criterion. If we meet some condition, okay, let's just stop the sifting process. And some numerical validations are currently ongoing, and the stream mechanism will also be introduced into our parallel implementation to further improve the parallelization and the performance. Thank you for your kind attention. That is our work about the MEMD. Thank you so much.
Thank you very much. Questions from the audience?
Well, I'm not an expert in this mode decomposition, but naively, what I would start with is you have a time signal. Maybe you apply a window function to cut off the edges, and then you do some Fourier transform and Fourier analysis. So And actually, in these simple figures, you also showed some harmonic waves at the different diamonds. So, what is the main advantage of this method compared to the naive?
Okay, thank you for your question. Basically, I would like to talk some details about the EMD, the empirical mode decomposition. As you mentioned, based on some window analysis, sometimes it will work, but in some special signals, such like the electroencephalogram signal, the EEG signal, the instantaneous frequency on each point are mixed, but we know that there are some fixed oscillation mode inside. In this case, some mode-based method cannot be used, and this MEMD can separate the oscillation mode from the raw signal, and that is the advantages of this method. And also, it's very time-consuming. It will take ages. So our purpose is to accelerate based on some parallel implementation on GPUs. Yeah, that's it.
Okay, further questions? I might have one. So what is this typical size of a real sample, what you would like to process with this method? So
well, our current work is the simple signal now is the EEG signal collected from the, well, actually it's from 32 channels signal, and from the 128 channels. It's basically it's about the EEG signal. Yeah.
Okay, thank you very much. Any further remarks or questions? I cannot see outside. Do we have something? No. Thank you very much.
Thank you.
So it's time to call the next speaker, who is also kind of very old colleague, participated with us from the very beginning, Geza Odor. He will speak about philosophical thing that what makes us human, differences in the critical dynamics underlying the human and the fruit fly connect.
Okay.
Please, Geza.
Thank you very much. And first of all, I would like to thank the organizers for scheduling my talk for today, because tomorrow I will have exams to be supervised. So as you see, I a little bit truncated the title, which was What Makes Us Humans. This nice but a little bit provocative title is coming from so the little bit provocative title coming from Gustavo Deco, who is head of Center of Brain Sciences at the University of Pompeu Fabra in Barcelona. And he also provided the possibility for us accessing the Barcelona Supercomputing Center for a while. So we had the chance to run our GPU codes on the Mare Nostrum machine as well, but most of the work, and I would like to appreciate, is done in the Hungarian KIFU Debrecen 2 Supercomputer Center. And another author, collaborator is also maybe well known within this GPU Day community is Jeffrey Kelling, who developed the CUDA C++ codes. In Germany, he is also head of a kind of GPU lab now in Helmholtz Center. Okay, so by the way, I am coming from MFA, which is the Institute of Technical Physics and Material Science within the Center of Energy Research. Okay, so what is it? Step. Oh, right. What does it react? I just push this. It was working. Okay, thank you. So okay, seems to work now. I mean, I can move the animations. So it will be mostly scientific talk on statistical physics, but let me begin first a sentence which is coming from the brain experiment. You can see here this little figure which was made by electrodes displaced on the human brain. It was done in 2003. And what you can see is the electric avalanches, the probability distributions of the electric avalanches on the log-log plot. And what was a little bit exciting at that time that they do not follow a simple Gaussian, but there is a tail with a power law tail. And power law tails occur usually in systems which are in a critical state between the activity and inactive state. And there is a hypothesis from that time which has been strengthened by many experiments and theoretical work that the brain should operate at this critical state where there is an optimal computational properties in this kind of system. And this may also apply to artificial intelligences, by the way. So this was the first introductory stuff. And, again, it doesn't go further. Okay. We also know that neurons exhibit oscillatory behavior. So therefore, we will investigate oscillatory modes, put on some huge brain networks. And the third thing is that besides this criticality, the brain and other neural systems are very inhomogeneous. And we know from statistical physics that this inhomogeneity, at least the static or quasi-static inhomogeneity, causes some kind of extended dynamical criticality extending in the parameter space, and these are called Griffiths phases in condensed matter physics. So the big question is the Griffiths phase at the edge of the synchronization transition? By the way, this critical transition also called the edge of chaos in nonlinear physics. So I try to answer this question by comparing the human and fruit fly connectome by the simple model. And this model is just the Kuramoto oscillator model. which here you can see rotating angles of and it is a very simple equation of motion you can see on the top. So you have the phases theta I, which are connected by the sign difference of the neighboring sides thetas with the sine function, and Wi is interconnection matrix, and there is a global coupling in the system. And okay, there is a adjacency matrix, and there is omega I0, which is the cell frequencies of the ith oscillator. So this is one of the simplest model of oscillator models, and we measure the averages of the e to the I thetas, which is the so-called Kuramoto order parameter, and also the frequency deviations from a peak. So originally we started from a sharp Gaussian frequencies of I0 omega of these oscillators. And what is known from this model, at least for Euclidean systems, that there is a transition in the model. So if the global coupling is greater than a threshold Kc, the R goes to a finite value. If you are below, then the R goes to 0, but it will stay finite due to the oscillations. So the finite value is 1 over square root of n, where n is the number of nodes. And if you just add Kc, you have power laws. For example, power laws asymptotically. If you start from an incoherent initial state, the R will go to the theta of power of eta. Okay, so roughly speaking, this is the model, and we implemented it with the help of Jeffrey, mainly on the GPU CODA code with the C++ using VexCL and Boost libraries, and originally Runge-Kutta 4 ordinary differential equation solver was added, but later now we extended with adaptive solvers. Lilla Baranchuk talked about in the previous GPU days, and we add more and more features and solvers. And we already had some nice results on the small world graphs and brain systems from 2019, which I presented here on the GPU days. And remind you, these human large graphs are coming from the MRI images, which has the 1 millimeter cube voxel resolution. So they have about 10 to the 5 to 10 to the 6 nodes. And these are hierarchical modular graphs. On the top level, you have the 70 brain region is from the Desiccant Atlas, and the lower levels are obtained by the deterministic tractography by the so-called FACT algorithm. And then you can make a mapping of the image voxels onto vertices, which are originally 10 to the 7, to the fibers to edges, which are originally 10 to the 10. And after some noise reduction, you get a graph which is undirected but weighted. Why do we need such a large graph? Because if you want to show really nice power laws in statistical physics, we want to avoid finite size effects. So we really need it. But you have to take into mind that these are structural graphs where the nodes already contain up to 10 to the 4 neurons. So these are the nodes do not correspond to neurons. And another thing that we found that there is a power law weight distribution of the edges, which was analyzed by us, by Michael Gessner in scientific reports. And so we took one of the representatives of these large graphs, which has something like 800,000 nodes and 41 million weighted edges, and run this Kuramoto model on it. We started from disordered state. And if you start from the disordered state, you can see that the R, the phase order parameter grows. If the coupling is large, there is an upward curvature. If the coupling parameter is small, there is a downward curvature, and in between, in this log-log plot at the blue line roughly, you can see some power laws. And okay, here in this inset you can see the steady state values as a function of k, the infinite time values. So here you have the unsynchronized states, and there is a synchronization transition occurs as k grows. And you have to observe that the dimension of this graph is less than 4, which is the critical dimension. So there is not a real phase transition here, but a crossover. And if you look at the blue line, as I said, and especially on the log-log plot, which I mean the local slope, which are plotted as a 1/t, you can read off the corresponding critical exponent, and the case equal 1.7, you find some exponent here. And one more thing, because of this wide distribution, we had to apply a kind of weight renormalization by dividing the weights by the sum of the incoming weight, and this was really necessary. It models the inhibitions and then the local homeostasis to suppress the hubs, which due to the weights you can have hubs in this model. So here you can see independent samples of the runs. So each line here is a corresponding of omega I0 self-frequency distribution, and you can see most of them are increasing if you are around criticality, but then they will jump back up to this value, which is this 1/√n corresponding to the inactive phase. And we measured the characteristic time of falling back to this threshold here. And after running 10,000 initial independent realization, histogramming, we plotted here these return times, probability distribution, and in the log-log plot you can see some kind of nice power law tails. At the critical point, you can read off the slope, which was about 1.2. But what is more interesting, that if you go below the critical point, k less than 1.6, you can see this non-universal power law trails, where the characteristic time exponent just falls within the range of some experimental values done for humans. Okay, so this is about the human part, and we published it. And now let me turn towards the fruit fly. The fruit fly is very interesting because it was published, and this is a real neuron level graph, which is, you can see this is the one quadrant of the fruit fly, which was mapped, and it has 21,000 nodes and about 3 million edges, but the dimension is much higher. It is not below 4, but it's about 5. And if you look at the structure, first of all, you can see that on the main plot, you have again this power law tails of a wide distribution, which is similar to the human graph. It might be effect of the learning. But what is a big difference is that there is much less structureless. So you can see this is the adjacency matrix, where black dots shows if A and J on the X and Y axis are connected or not. So this structure is much weaker than in the human graph. In fact, if you measure the modularity quotients, it turns out that the fruit fly has 40 times smaller modularity than the human graph. Okay, so what's the consequence of this? The consequence of the dimension of this is if you make the same Kuramoto runs as for the human graph, you will see a phase transition again. You can read of a point, but at the point the exponent will be a single value, and the exponent will correspond mean field approximation value, which is valid to very, very large, high dimensional spaces. And besides, if you plot the probability distributions of these return times multiplied by t to the power of 1.6, which is the mean field case, if you had some power loss, you should see some plateaus, but you don't see too much plateaus there or power loss, only the mean field value. So what does it mean? It means that these fruit fly results are very similar to the completely random so-called Erdős-Rényi graph results. These are the similar size random network results, where we really only have a criticality at the transition, but away do not. And one more thing. We have measured the fluctuations of the order parameter. So this shows, for example, of the fluctuation of the phase order parameter for different models as the function of coupling. So the bigger is the peak, it means it's more chaotic. So you have a chaoticity to the transition point. And you can see that the fly and the random networks have the black and red, a very similar peak structure as compared to the KKI-18, which is the human graph, which is a very, very small smart transition chaoticity. And this here we really needed to run the adaptive solver, which made it available, I mean, possible to do it with the help of the supercomputers and GPU cards. Okay, so again, we also tested inhibitors, but I don't go into the details, just to show that for the other order parameter, which is the frequency spread, you can also see this chaoticity peak, and in principle the same conclusions. In the human case, you have a much more extended dynamical scaling. This means that here the sensitivity is maximum, okay, which is very important for neural systems. And another interpretation is that if you are in between this active-inactive transition, due to the heterogeneity, you have this Griffiths phase, which is caused by the rare regions which are more connected. Okay, so let me just show one animation, which is thanks to Shangfeng Guan, who is here in the audience, and he will present similar results on power grids tomorrow, and he will show beautiful pictures, I hope, on the whole European high voltage power grids, which we also solved by Kuramoto model. But this here you can see the local order parameters. So we did not sum up these different phases for the whole system, but only for the neighbors coupled for a node. And these are the local Kuramoto results by color coding on the top. Okay, so you can see how, as the function of time, different more synchronized regions appear within the fruit fly connectome, and then you can see some chimera states possible and chaotic behavior. Okay, we are under current research to investigate this turbulence or chaotic phases here. Okay, just let me go to the conclusions. So the almost module-free network of the fruit fly with the high dimensions causes mean field-like synchronization criticality, as in case of the Erdős-Rényi model. In case of the human networks, the dimension is 4, below 4, it's about 3.1. And we can see this extended region of dynamical criticality with continuously changing exponent. And this is what we were referring to, what makes us humans different from other, at least low-level animals, but we can test it by monkeys, for example. Maybe show this, we haven't done it yet. And the exponents agreed with this long-range temporal correlation experiment, the Finnish group. And just for implementation, unfortunately, I don't have really nice benchmarks, but maybe Changfeng could show it. My measurements were done on the GPU A100 or V100. It was 100 times faster with a single CPU core. So even though the graph is very, how to say, irregular, and not really good for the GPU architecture, we could see really good speed ups. Okay, and if you are interested in the details, we have a publication just appeared in Physical Review Research this year, and previous year in Eurocomputing, and we also published the journal Physics in Complexity, a review journal. And finally, we have an advertisement. If somebody is interested in to join our team, unfortunately, we now have a PhD and a postdoc position starting from at our department from September. So we'll be welcome, especially those who have GPU computing interest or knowledge. And thank you for your attention.
Thank you very much, Geza. So, questions from the audience?
Okay, Geza, this is very exciting, but I think I missed something. The model is based on structural connectivity graph, right?
Yeah.
Which is mainly static.
Yeah.
So where is the phase and dynamicity coming from? In this one, you have a neural model underneath, or what?
We use the Kuramoto model. Okay, and the Kuramoto model has two phases. If the coupling is strong, there is a strongly coupled synchronization phase, and if the coupling is weak, you have a non-synchronized phase. So these are the big phases.
Yeah, I don't know the model. This is I'm lost a little bit. So what is happening in the model on the graph? Is this some signal propagation that you're simulating? Or?
Synchronization. So there are oscillators on the nodes, and if the coupling is strong, they synchronize. Like in this little, I can go back about this Wikipedia.
So basically, you have an equation for each node.
Exactly. I is the node number, so there is a set of ordinary differential equations which are running on each node, right? And they are coupled. So coupled.
So would it be possible to use this not as a, let's say, as a simulation model, but on real measurement, on dynamic graphs?
Dynamic graphs, that would be really a hard stuff, because at the moment we hardly have static graphs or very small ones. But theoretically, it could be done on dynamical graph, but we are happy just to use the quasi-static approximation at the moment.
Okay, great. Thank you.
Okay, further questions?
If I recall, you said that in the current data, the KKI18, that was the name. It's 1 cubic millimeter for every voxel, which is roughly 1,000 neurons inside. Yeah. And for your research, if technology would wave its magic wand and that size could be reduced by an order of magnitude, or 2 orders of magnitude, so that it's not a voxel average of 1,000 neurons, but 100, let's say 10 neurons. Would it still be feasible to calculate these kinds of investigations?
Are you asking if the GPU technology will cope with the increasing the simulation size by several orders of magnitude of resolution? This is the question.
Like for such an investigation, you showed that on 1/800 it had some critical speed up, but what fraction of an 800 is being used in these calculations? Like how compute bound or memory bound is this investigation?
I think Jeffrey could answer this question. It depends on him. In the human graph, I don't want to say improvised, but he wrote something that it was memory bound somehow. But I guess from the smaller graphs like the power grid graphs, we have much smaller systems where will be with the memory bandwidth. But okay, it's a very irregular graph. So obviously the communication is a big problem, because you can have access a very large node which can be very far away. Unfortunately, Jeffrey made a lot of optimizations for the propagation of signals, so could order some nodes in such a way that the communication is not so bad. Yeah.
Okay, thank you. Is it a question or no? Okay, so thank you very much, Geza. And now it's time for lunch. So those who are familiar with the place, you know where the restaurant is. Maybe Gabor can lead you to downstairs, and we will come back to here at 2 sharp when we're going to start. And I asked the afternoon speakers to upload the talk, either giving us to here or uploading to the Indico site. Thank you very much. Bon appetit. Hi, David. This is Gergely speaking. Can you hear me? David, can you hear me? This is Gergely speaking.
Hi, this is David. I can hear you.
Yeah, okay, excellent. So now we have your voice. Can you give me a video as well, just to see if it's working?
Yeah, it should work. I can also share the slides. You give me a second. Oh, I don't know. Shall I share or will you share?
Yeah, I'm here.
Okay.
Yeah.
Okay, hi. So now you should have the slides. Let's share as well.
So we can see the slides well. Okay. So this, it seems it's working well. Okay. Right.
Okay, and it's 30 minutes plus 10 minutes questions, or how is it?
5 minutes for questions. Yes, that's the point. Okay. Okay. Thank you. I'm trying to get others. Thanks.
Hi, everyone. Good afternoon. I hope you enjoyed the lunch break. Now let's start our first afternoon session with David. David, can you hear us?
Yes, I can hear you. Can you hear me?
Yes, great.
Okay.
Can you share your slide?
Yep. Well,
yeah,
can you see them? Perfect.
Yep. So the stage is yours.
Okay, then let's start. So this talk will be about the usage of GPUs in the real-time data processing in the ALICE experiment at CERN during LHC Run 3, which is the data taking period that has started or is starting basically right now. To give you a bit of an overview of what we are doing at ALICE. So here in the background, you see more or less the data that we collect in the detector. So it's, I mean, LHC is a particle accelerator, so we collide particles. At every collision, thousands of new particles emerge, which fly in all directions. And we try to basically measure and identify them. And so the specialty of ALICE is that we use a drift detector. So the detector has quite a long time to read out the data, basically, that is created by one of the particle collisions. And that means that during this readout time for one collision, the next collision already occurs, which means that in the data that we are getting from the detector, we don't see a single collision, but we see multiple collisions overlapping. And that is more or less what is visualized here. So you see all the individual collisions in different colors. And then you can see that these collisions, they overlap more or less, but they are all shifted a bit in one of the geometrical directions. So if you look at the leftmost part, you see mostly green, which is the first collision. And if you then go a bit to the right, you see that the next collision in purple starts and so on. So we have many collisions. They overlap in the volume and in time. And I mean, this is just from the technique that we use for the data taking. And then I said it's LHC Run 3. So of course there have been LHC Run 1 and Run 2 before. And for Run 3, ALICE did significant updates, and I've just slightly, I mean, very briefly summarized what we did here. So beforehand, ALICE was not recording all of the collisions, but there were hardware trigger detectors that were doing a quick evaluation whether the collision is interesting or not, and then decided whether to read it out or not. So this is gone. So with the new experiment, we are basically reading out all of the detectors, what we call continuous readout. And then, as I mentioned, we have this overlap of the collisions in the detector. So we cannot record individual collisions, but we record what we call time frames. And a time frame is just, well, a certain period of time and then all data that falls into that. So the default for us will be 10 milliseconds for the time frame. And just to give you an impression of the data rates, we will see we will record 50 times more collisions that we collected in the previous run. So we will have obviously 50 times more data. And since the storage capacity does not increase by a factor of 50, we need better methods to store the data, which means we have to do online compression. And that requires a lot of computing. And for this, yeah, that's where the GPUs comes in. So we do the online processing on the GPUs for reconstruction and for computing. Then, well, how does the ALICE detector look like? So this is a schematic overview. You can actually see in the center of the detector, that's actually where the particle collides. And in this example here, you see two particles that are emerging in the center, and then they are flying outwards. And they fly not in a straight line, but on a curved trajectory because the particles are charged and they fly in a magnetic field. So you have the Lorentz force, which bends them basically. And then inward out, we have multiple detectors that can track the particles on their way out. So the innermost is ITS, inner tracking system, which is 7 layers of silicon pixel detectors. Then the next in that chain of detectors is the TPC, time projection chamber. This is actually the largest detector of ALICE. So it's a gas drift detector, which has 150 readout pad rows where the particles can leave a trace. And then afterwards, there comes the TRD, which stands for transition radiation detector, which has, again, 6 layers where the particle can be measured. And the last one is TOF, which is time of flight. And basically, in all of these layers, in all of the detectors, the particles leave traces, which we call hits. These are the stars that you see in the diagram here. And then the task that we have to do computationally is collect these hits to the trajectories. But then, of course, this is a quite simple example with only 2 tracks. And if you look back at the previous example that I've shown here, was well, several million tracks actually in the time frame, then you see that's computationally, of course, a quite significant challenge. Yeah, okay. So that is a bit as an introduction and for the geometry of the detector, and I hope you have a rough idea of what we are doing. But really the challenge computationally is to process in real time the data that comes from this detector and do data compression. Okay, and go a bit into more detail what we are doing. So we have to separate a bit what we are doing online, so while the experiment is running in real time, and what we are doing asynchronously when the experiment is not running. So for the online part, when the experiment is running, there are two main purposes of the online system. So the first is detector calibration. So I'm not going into too much detail, but one example is that the charge created inside this detector creates an electric field, and the electric field distorts the particles during the drift, and that basically distorts the projection that we get from the drift. So we have to measure this charge and compute correction maps to correct for these distortions. And so that is basically something that has to be done before we can properly reconstruct the events that we have recorded, because otherwise everything is so distorted that you basically lack 10 centimeters or so in precision resolution, so there's no chance to reconstruct. So calibration is quite an important thing. So that happens, I mean, we have steps online during the data taking where calibration information is stored, which is then later needed for the final reconstruction of the data. And the second quite important aspect of the online processing is what I already mentioned, so the data compression. And one technique that we use here for the data compression is that we do not store absolute positions of the hits, but we store the positions of the hits relative to the trajectories. And that is a bit shown in the picture on the right in the middle. So you see the particle trajectory in blue, and then you see all the hits in yellow, but because of the distortions, the hits don't follow exactly the perfect trajectory. But what we can do now is, instead of storing the absolute coordinates of all the yellow hits, we can store the parameters of the blue trajectory, so basically one position, momentum vector, and curvature. And then for each of the yellow hits, we can store only the relative residual from the hit to the track at that X position, for instance. And that reduces the entropy of this data significantly, and then we can use entropy encoding like Huffman or ANS encoding to compress the data significantly. However, that means, of course, that we need the trajectory of the particle, which means we have to run the tracking. So finding the trajectories out of the hits, we have to run that in real time to do the data compression. And that basically creates the third pillar of the online processing, which is the event reconstruction. So in order to do the calibration and the compression, we have to reconstruct, at least in a kind of uncalibrated way, so with reduced precision, we have to reconstruct a full event in real time. So the reconstruction itself is, of course, also important for quality assurance and control, but the main purpose to reconstruct really everything in online is data compression and calibration. And then, as I said, we have this asynchronous processing. So what happens not while the experiment is running, but when there is no beam in the LHC, so no particles colliding. And then we use the same computing resources that we have for the full processing of the data with the final calibration. Okay, to guide you a bit through the computing setup that we have. So the computing is happening in what we call the O² project. That stands for online offline processing, because we do the real time and also the asynchronous one. And the hardware is divided in two processing farms. So we have one farm which we call FLP, which is positioned in this what we call CR1, which consists of 202 servers. And these servers, they do the readout, so they receive the data from the detector with optical links, and then they do the local processing of the data on CPUs and the FPGAs. So FPGAs, they are the custom readout boards that we have, which receive the optical links and which then can do some local processing, something like zero suppression. So quite simple processing usually. And then the second farm is the EPN, so event processing nodes. And that is where the bulk of the processing happens. So here we have 2,000 GPUs in total, 250 servers, so 8 GPUs per server. And here we do the majority of the processing. To show you a bit the data rates, so we send up the data from the cavern where the experiment is to the CR1, where the first computing farm sits at a data rate of 3.5 terabytes per second. Then here we have the local processing in the FPGAs, which does zero suppression and reduces the data rate to 635 gigabyte per second, which is then sent via the InfiniBand network to the CR1 computing center where the EPNs live. And here we do the calibration and compression now on using the GPUs, reducing the data rate to 100 gigabytes per second. And then we store 100 gigabytes per second worth of compressed raw data. This is called CTF compressed time frame. This is stored, well, first to a disk buffer, and then later it's migrated to tape. And of course, the calibration data is stored as well. So this was the overview of what is happening during the synchronous processing. So we have local event processing, building of the time frame, so aggregating the elements of all the individual links and running calibration and reconstruction. So now when there is no data in the LHC, as I said before, we do asynchronous processing. And what we do here is we basically load the data that we stored on the disk buffer back into the data center. So here we have the disk buffer, and then we read back the compressed timeframes into the computing center using the 2000 GPUs for the processing. And then with that, we create the final reconstruction object, which is called AOD. And now, of course, this doesn't have to happen in real time, so we can accept some latencies. And I also said that the data is migrated to tape storage at the CERN grid data centers. So it's not necessary that the whole reconstruction runs in this online computing farm, but the part of it can also run somewhere else. So there's the CERN Worldwide Computing Grid, WLCG, which has lots of compute power. So part of this asynchronous reconstruction will happen there, reading the data from the tape, also creating the AODs. Okay, and as I said before, so the processing steps during this asynchronous reconstruction is now just the full processing with the final calibration available. Okay, and this is just a summary slide with what I said. So with these two steps, so first we have the synchronous and then we have the asynchronous processing. So I'm not going into too much detail here. I just want to emphasize that the synchronous processing is the important thing for the data taking, because this really has to happen in real time. If we don't do that, there's no way we can store the 3.5 terabytes per second that we get while the experiment runs. So this has to work in with the given compute resources that we have in this farm. For the asynchronous processing, we are a bit more flexible since, as I said before, we can use the CERN computing grid. And okay, so therefore we have kind of separated our reconstruction tasks in two categories. So some of them belong to the baseline scenario, and the baseline scenario and that comprises everything that is really needed for the synchronous processing. Basically, if we fail to deliver the baseline scenario, then the experiment cannot run. But then, of course, we have the GPUs in the data center, and we want to use the data center also for this asynchronous reconstruction, which means we should develop all the software steps of the asynchronous reconstruction such that they can use the GPUs efficiently. And doing that, we call the optimistic scenario. And of course, there are many reconstruction steps, and we were looking a bit which are the best parts to run on the GPU, and that is what we call the barrel tracking chain. So the barrel tracking is the track reconstruction for all the detectors that I was showing on the second slide in this barrel region, which looks like a barrel. That's the name. Okay, and in this in this plot, it's basically a directed graph with many blocks corresponding to different processing steps that we have. And here we see that they belong to the baseline scenario or the optimistic scenario. And then, of course, so here it's again highlighting everything that belongs to the baseline. And then, of course, we also have the synchronous and the asynchronous. And one special thing of the synchronous is that certain tasks we only have to run on a small fraction of the events, because, for instance, calibration, it is enough if we calibrate only 1% of the tracks, with that we get enough calibration. So some of the things actually they run in the synchronous, but they are not essentially necessary for the baseline, because they if we couldn't run them efficiently on the GPU, the processors would still be sufficiently fast for them. That's why we separate a bit here. But so basically what is highlighted here now is what is running in the synchronous reconstruction. And then what is highlighted in this plot is the asynchronous reconstruction. And basically what is missing here is the stuff that comes, that branches up to the upper part, which is basically everything that belongs to the data compression. because the data compression happens synchronously in real time when the experiment is running. But then when we run the final reconstruction and the asynchronous processing, we of course don't have to compress the data anymore. We just read the compressed data and process it. So this compression part is completely missing. Okay, so coming a bit more into the details for the GPU processing. So I think one important thing is that, I mean, if you looked at the plot before, you saw that there are many individual boxes. And okay, at the beginning, some of them could run on the GPU, some of them could run on the processor. And this was really a problem because we had to transfer the data forth and back between the processor and the GPU. And so on the host processing side, using the CPUs, the idea is that we have shared buffers between the individual steps, so we don't have to copy stuff. So there's every process has an output buffer that is then shared as an input buffer for the next one, and then it's basically zero copy. And we try to do the same thing with the GPUs, so to keep the structure of individual components, which also makes us flexible, so we can enable or disable individual processes. And then we have shared buffers on the GPU memory in between them, and the components run one after another. Each writes its output to a shared buffer, and the next component is reading from there. And then we try to have consecutive steps in this processing chain on the GPU, such that the data from the host buffer to the GPU, the copy from the host buffer to the GPU buffer, which you see here at the very beginning. So from this shared buffer to this shared buffer, this has to happen only once at the very beginning, and the same for the output, because otherwise we are a bit lost in the transfer forth and back. So I think that is one important paradigm that we have been following. And the second is that we try to use a generic common C++ code that is not coupled to any particular vendor or API. So the GPU code that we have is just more or less C++ with some custom preprocessor defines, which then using some backends go to either the CUDA, the OpenCL, the HIP, or you tell me what backend. But the algorithm itself should be more or less generic. And okay, so then there are some particularities. I don't want to go into too much detail, but in the figure on the lower right, you see a bit how this is done. So we have one file which is shown in the block in the upper left here, which is the algorithm CXX, which contains a function that does something on the GPU. In that case, it's a function that fits one track. So it's called fit track. We get the index of the track in there, and then we have this preprocessor macro GPU in front, which is then translated to either CUDA, OpenCL, or whatever keyword. And then we have different libraries which all include this file. And before they include it, they define the preprocessor macro GPU to something that is needed. So for the host, it will just be defined empty. For CUDA, it will be defined to __ device for a device function, and you have something similar for OpenCL. And then this file is basically compiled multiple times, and each time it ends up in a different library, and then one of them can run on the processor, one can run with CUDA, one can run with OpenCL. And the second thing that I want to highlight here is that the approach with these different libraries also allows us to deploy the same binary code on multiple different servers, which can be heterogeneous. So if we have some servers that have NVIDIA GPUs and they have the NVIDIA driver and everything available, they can run the libfit CUDA. And something else that maybe has OpenCL can run the libfit OpenCL. But something that doesn't have GPUs and not the drivers can actually maybe not even load this libfit CUDA library because it's statically linked to libCUDA. And if CUDA is not installed, we cannot even load that library. So what we do is we have a DLOpen interface, which dynamically opens these libraries at runtime, and it's not linked at compile time. And what we can do is we load the CPU library, and then we can request the CPU library to load one of the GPU libraries basically as a plugin. And the interface is always the same. The same libraries are distributed to all of the nodes, and those that have GPUs, they load the GPU libraries at runtime and use the GPUs. And that has turned out to be quite flexible for us. And okay, then here on the left, there's a summary with all the GPU models that we support. So we have processors, we have GPUs of AMD and NVIDIA. Actually, we didn't do much with Intel yet with the one API. We might look into that, but so we support OpenCL at least, and that means we can run on the ARM Mali GPU of my smartphone, for instance, although that's not so important, of course. Okay, so coming to the next topic for the GPU part, that is memory. So I mean, the important thing is that we have to process timeframes. So as I showed at the very first slide, we have the overlap of many collisions in the timeframes. And we cannot disentangle the collisions ahead of time, because really only after the tracking is done, we can assign the individual data to the individual collisions, because they just overlap. Which means we have to process the time frame at once, in one go. We cannot split it in two parts. So the whole time frame has to fit in GPU memory, which is a bit different to many other high energy physics experiments, because they don't have these drift detectors, so they really have many collisions. And they actually have the problem that individual collisions might be too small. While for us, the problem is completely the other way around, that the time frame might be too large. And yeah, so how we do that is that we just grab all the GPU memory that's available, and then we have a custom allocator that gives the memory to the individual processing steps. And okay, it's a bit simplified what I'm showing here, but basically we take chunks of memory and then we split them into persistent and non-persisting data. I mean, one implementation is that we just fill the buffer from the left and from the right with blocks. And the persistent data is data that will be needed for the following reconstruction steps, so they will remain in the buffer. And the non-persistent data on the right is data that will be removed after the current processing step has been running. And so then if we go through the processing, so this is all the processing of the same time frame, we have more and more processing steps running. Some of them can allocate scratch data, which is allocated somewhere in memory in addition, and then freed again. And you see that on the left side, the persistent data fills up, while the non-persistent data on the right side gets removed step by step. It's not always, let's say, completely tight. So there might be gaps also in the persistent data of memory that is then lost, and we cannot fill in something because we don't do virtual memory or whatever. But I mean, it's a quite simple scheme, but it works for us. And then, of course, the important thing is we don't want to make the GPU idle. So at the end of the processing of one time frame, we can already preload the non-persistent input data for the next time frame, such that we basically overlap the processing and the data transfer. So when the processing for one time frame is done, we can start with the next one immediately, which basically gives us 100% GPU utilization. Okay, so looking a bit at benchmarks, comparing GPU performance of different models and with the processor. So okay, what we see here is two different plots. So on the right side, we see the processing time of different GPU models versus the input data size on the X scale. So the X scale is basically the size of the time frame, and if the time frame is larger, then we have more tracks, and it's obvious that the processing time goes up with that. And the important aspect here is that this increases linear. So if we have a time frame that is twice as long, the processing of it takes exactly twice as long. And if we would have, of course, any quadratic dependency here or something like that, then it would be a kind of disaster, because then with the large time frames we have, this would not work. So this is quite important that it's linear. And the plot on the left side shows a comparison to the CPU. So here we show basically how many CPU cores. So as a reference, we took a AMD Rome core of 3.3 gigahertz. And so the plot shows how many CPU cores are replaced by a single GPU. And then again, we have different GPU types here. What I want to mention, of course, is that the algorithm we have used here, this is quite optimized for GPUs. So for instance, the MI50 GPU replaces 80 of the AMD Rome cores, which is not really representative of the relative performance ratio of the GPU and CPU, because there are steps in here which are heavily optimized for a GPU and don't work well on the processor. So if we restrict this benchmark to the asynchronous reconstruction steps, not the synchronous one, and the asynchronous ones are more optimized for the processor, then this factor goes down from 80 to 55. So I think this is the more realistic number for us. Okay, just to mention, so for this benchmark, what we did is basically we take one time frame and we run this in a loop as fast as possible to see how fast the GPU can process it. But this is, of course, not how our system operates. In the system we have 250 servers, and we have data published by the detector, and then the data is shipped to the nodes, and they have to process the data as fast as they are coming in. And of course, there are latencies and everything, and this has to be considered. So to test this, we do what we call the full system test. So we have one server with all the 8 GPUs in it. It has 64 processor cores and in total and 512 gigabytes of memory. And then I mean, in total, we have 250 servers. So this is one server which we are measuring. So we are sending 1/250 of the total data to this one server and make it process it. And then we see how it goes. And the two plots you see here is showing the CPU load in terms of number of CPU cores used on the left. And on the right side, you see the free memory in the different memory buffers that we have. And so, okay, now there's two important aspects here. So the first is we shouldn't use all of the CPU cores, of course, because we need some margin. And the maximum we have here is 44 cores. We have 64 available, so there's sufficient margin, I would say. And on the right side, the important thing is that after some, well, startup phase, which takes, in this case, actually, well, 90 seconds, so 1.5 minutes, the buffer utilization is stable. And that shows that the server can process the data as fast as it is coming in. Because if the processing would basically be too slow, then data would be coming in faster, so the input buffers would aggregate, and we would see that over time the remaining buffer size would go to 0, and then we would have back pressure where the server cannot process the data fast enough. But this is not the case. The buffer utilization is stable. So basically the farm that we have can operate with the data rate we are getting from the experiment. Okay, and then of course we do all the monitoring for GPUs. So this shows the temperature. So this shows the temperature of the 8 GPUs in one server, and you see actually a lot of up-down. And this up-down is that, of course, we have some margin in the processing. So we would need 220, 230 of the servers, but we have 250. So the publishing rate is a bit lower than what a server could do. So there is some idle time in the GPU where the GPU is not doing anything but waiting for the next time frame. And that is actually enough for the GPU to cool down significantly, and that causes these oscillations that you see here. Okay, then I think the last topic I want to focus on is, so it's quite important for us to offload the asynchronous reconstruction steps to GPU to make better use of the GPUs during this asynchronous reconstruction when there is no beam. And the question is a bit, which steps do you want to offload to the GPU? So of course, we cannot put everything on the GPU because we have some small detectors. They are responsible for 1 per mil of the total processing time. So it doesn't make sense to put that on the GPU because it would just be a waste of manpower basically to port the code. So what we did is, and this, I mean, the measurement is quite old. It's from 1 year ago, and unfortunately we didn't put much effort to improving it. But basically we measured the relative time of each of the reconstruction steps on the processor, just to see what has the highest compute load relatively to the others. And then, of course, those are the best candidates to offload to the GPU. And I'm showing one old slide here. As I said, it's 1 year old. And then you see that for the synchronous processing, in green, you have what is already running on the GPU. In yellow, you have what is running. Well, it wasn't running back then, but now it's running. And then you see for the synchronous processing, we are more than 99% that is running on the GPU. So that's basically everything. And for the asynchronous processing, if you sum that up, then it's more than 85%. However, this is a bit tricky to evaluate because this relative time depends a bit on the multi-threading. So we have the 64 processor cores, and then we have these reconstruction steps. And we can, of course, run all of them single-threaded, or we can do multi-threading inside the individual steps, because as I showed you before, we can use, for instance, OpenMP in the same way we use GPUs. So we can parallelize inside the steps. But now the efficiency of this parallelization is not the same for all of the reconstruction steps. And that, of course, changes the relative compute time each of this reconstruction step takes. And so we can do 2 corner cases, basically. The first corner case is that we do full parallelization inside each step. So we run one step after another, and each step takes all the CPU cores it has available. And if we do that, the fraction that we can offload to GPU already is 85%. But this is not the optimal processing way the CPU can run. And so for that, we have tried a second corner case, and here we do everything single-threaded. And the single-threaded basically reduces the time of the heavy parallel processing things, because whatever is processing in parallel basically has some scalability loss. And so if we run it single-threaded, it's in some sense more efficient, at least relative to the single-threaded peak performance. And okay, so if we do this, and then we do the same measurement, and it's only 60% that can be offloaded to the GPU. However, the single-threaded running is nothing we can do because we would just use too much memory. Because as I told you before, the timeframes are large. We have 64 cores. We cannot process 64 timeframes in parallel single-threaded. So that would not work. So basically, this would be the fastest case for the CPU, but this is not something we can run. So the reality is somewhere between the 60% and 85%. And we are still working to basically tune the CPU software to get a proper answer. What is the final correct number of, or the final correct fraction of the workload that can run on the GPU. But it's between 60 and 85%. Okay, and with that, I'm at the summary. So what we call OSquare, online offline processing, is the online computing scheme that Alice uses for the current data taking run, and includes the update of the hardware and of the software of the full computing infrastructure. We have two reconstruction steps. So we have the online step, which we call synchronous processing, which happens while the experiment is running, doing calibration and data compression. And then we have the full reconstruction with the final calibration, which is happening asynchronously when there's no beam in the LHC. We use GPUs for the bulk of the processing. In the synchronous phase, we have, I mean, here's 95, but I think in total it's more than 99% of the processing happening on the GPU. And in the asynchronous phase, it's been between 60 and 85%, depending on how you measure. And I want to emphasize there's also some local processing not on the GPU, so we use processors and FPGAs for that. And okay, we did this full system test, so we know that the system we have is fast enough to cope with the highest data rates we expect, with 20% margin. And in the first commissioning data taking beams that happened already at LHC, this was proving to be stable. And yeah, one important aspect is that we are independent from vendors, so we can run with different GPU types using CUDA, OpenCL, or ROCm. And with the synchronous processing, we are basically mostly done with the optimization, and now we are aiming to optimize the asynchronous processing. Okay, so that's it. And yeah, thanks for the invitation, and I'm happy to answer questions.
Thank you very much, David, for the very nice talk. So questions from the audience? Yes?
On one of the slides where you were showing the how many CPU cores does a given GPU substitute? Yes, this one's. You're showing that and you mentioned the MI50 in particular, how in the synchronous and asynchronous cases it replaces 80 ROM cores, but it's more realistic that the asynchronous workload, which is properly optimized for the CPU, only it replaces 55 CPU cores. So does that mean that if we are looking at efficiency on a socket per socket basis, like measuring the peak power draw of an MI50 and the power draw of 55 CPU cores, that the efficiency of processing in both cases is roughly on the same order of magnitude?
I would assume so. I mean, you cannot take the TDP because the software is not linear algebra software. So we are more bound by memory latency, basically. So we don't drive the GPUs at the 250 watts they are specified. It's more like 150. So you would need to do the real measurement. And I think the GPU would be a bit more efficient than the processor still, because the processor also has to use, it's not only the socket, right? You also have to count in the memory and the mainboard, etc. So I think the GPU would still be like factor 2 better, but not the usual factors that you see maybe. But I think one important aspect is that we put basically 8 GPUs into one server in order to leverage the server has a constant offset for power consumption and for cost, because we have to buy the server in any case. So the more GPUs we put in there, the better we utilize the infrastructure, I would say.
I tried to compress the question, but yes, like putting 8 GPUs does reduce the burden on like how large the network has to be scaled, and it does reduce the fixed cost of the nodes. But yeah, thanks.
Any more questions? Yeah.
This looks like a really big software project or large effort. So I'm just wondering, how long has it been going on, and how many people or developers worked on it, and what % of the effort went into the GPU part?
So I think we don't have many really full-time developers, but of course we had a lot of doctoral student, postdocs, whatever, that were doing GPU at some point. I would say it was always between 5 and 7, 8 people that were working on the GPU, but most of them not full-time, maybe 1 or 2 full-time. In terms of the code size, I think what is running on a GPU is not negligible. So it's certain, I don't know, a few 10,000 lines of code maybe. But compared to the whole software, which is more order of 1 million lines of code, it's of course not much, because we have many processing steps that just don't need the GPU, because they just do something once, they are for simulation, for preparation of something. So they don't need much compute time. So that, of course, is not moved to the GPU. So from the total code base, I think it's a small fraction, but it's still absolutely, it's a significant amount of lines of code.
Thanks. Any more questions? Yes.
Hi. I have actually 2 questions. One would be, so does it mean that now you can completely circumvent the triggering and the hardware triggering that was used in earlier experiments? It was a key factor to store the data. And the second would be you mentioned that you have InfiniBand between the first CR1 and CR0, but what about the network fabric for the raw data, for the 3.5 terabytes per second? Is that some special thing?
Okay, so for the second question, it's a custom link. Actually, there are different link types, but the majority of the data is a custom link, which is GBT, which is a radiation hard link that is developed by CERN for pumping data with optical links from the experiments to the data centers. I think it operates at 6 gigabit per second. So actually, compared to something like InfiniBand, it's not extremely fast, but it's also robust and radiation hard. And then, of course, we have hundreds of fibers going up from the experiment. So that is all custom. And okay, I forgot the first question. Can you repeat?
So this method you can use, you can forget about the triggering which was used.
Yes. So the point is basically that ALICE is looking in rare physics cases with a lot of background, and then we have the overlapping of multiple collisions in the TPC anyway. So if you would trigger, you would have to trigger quite often because the background is that high. And if you trigger and you read out the TPC, you anyway don't read out a single collision because they are overlapping. So it doesn't make sense. If you would try to trigger, you would maybe read out half of the data, and now we are reading out all of the data, but we have much more minimum bias data set.
Thank you. If there are no more questions, then thank you, David, again. And our next speaker will be Suraj Prasad. Suraj, can you hear us?
Hello. Yes, I can hear you. Can you hear me?
Can you share your slides?
Yes. Okay, so.
Yes. Perfect. Go ahead.
Thank you. Hello, everyone. I'm Suraj Prasad. I'm PhD student at Indian Institute of Technology in India. So the topic of my presentation will be machine learning based estimator for elliptic flow in heavy-ion collisions. So this presentation is based on this work. So going to the outline of my talk will be, first I will discuss about the heavy-ion collisions and Park-Borg plasma. Then I'll talk about the elliptic flow, then discuss about the deep neural network, give general idea about deep neural network, then I'll talk about the inputs that I have been taken in my work, then the TNR architecture of my work, then quality assurance results, and finally I'll summarize the works. Okay, so as you know that the solids and solid, liquid, and gases are composed of molecules and atoms. So if you go further, subdivide the atoms, you will find that they consist of nucleus and electrons. Inside nucleus, there are nucleons such as protons and neutrons, so which are actually baryons and are part of hadrons. So there are also mesons And if you subdivide this, if you want to try to probe the substructure of these variants and mesons using very high frequency particles, so we'll find that these nucleons, hadrons are composed of quarks and gluons. So quarks are fundamental bits of matter, and gluons are the mediators for strong interaction. So quarks and gluons have color degrees of freedom and cannot exist freely. But as you might know that the universe started from Big Bang and evolved through states of phases, and quark-gluon plasma existed after a certain few microseconds after the Big Bang. So the quark-gluon plasma is a state having deconfined quarks and gluons in thermal equilibrium. So the quarks and gluons cannot be existed in pure state, but in quark-gluon plasma phase they exist in deconfined state. So how do we create this quark-gluon plasma? So quark-gluon plasma can be created by either going to the high baryon density or very high temperatures, or we should have both the conditions satisfied. So in Large Hadron Collider, what we do is to collide two heavy nuclei such as gold, lead, etc. At Large Hadron Collider, we actually collide lead nuclei, and after the collision of lead nucleus, so there exists a pre-equilibrium phase, and after a few Fermi seconds, the quark-gluon plasma exists. So quark-gluon plasma goes through phases of evolution, and finally the particles such as pions, kaons, baryons, and mesons are detected into the detectors. So the elliptic flow is an observable, which is the result of the hydrodynamic nature of the this quark-gluon plasma state. So before talking about the elliptic flow coefficient, I would like to introduce some relativistic Hebbian observables that will be used in this study. So suppose two particles collide and the particle is emitted at momentum p from the point of collision. So this p can be sliced into transverse part and longitudinal part. So the angle between this transverse momentum pt, which x-axis is the phi, azimuthal angle phi, and this theta will be the polar angle. So we can define rapidity as this half of log E plus pz by E minus pz, where E will be the energy of the emitted particle. Similarly, zero rapidity, theta will be minus log of 10 theta by 2. So the reaction panel angle psi r will be the angle made by this impact parameter vector with x-axis. So in non-central collisions, the overlap region of two colliding nuclei is not spherical, but it is ellipsoidal in shape. So if the initial spatial anisotropy is ellipsoidal, so this will transform into the final momentum of space azimuthal anisotropy due to the high pressure gradient created during this collision of matter. The anisotropic flow is defined as the hydrodynamic response to the spatial deformation of the initial density profile, and it can be demonstrated as the Fourier coefficient of the Fourier transform of momentum distribution. So this V1 is known as directed flow, this V2 is known as elliptic flow, and so on. So the motivation of this study is to see the estimate elliptic flow coefficient with with DNN. So this V2 can be calculated as mean of cos 2 phi minus psi 2, where psi 2 is the event plane angle, second event plane angle. So let's now discuss the deep neural network, the architecture of general deep neural network. So deep neural network is a machine learning algorithm which is inspired by the structure of neurons in animal brain. So there are three key layers. So input layer, hidden layer, and one output layer. So there may be one and two or more hidden layers. So input layer, what it does is take the different features as inputs. Then this hidden layer takes the features from input layer and connects to different neurons or to weights, and the output layers gives us the results. Suppose there is one input layer with 3 nodes, 2 hidden layers with 4 nodes, and one output layer. Okay, so this X will be taken as input by the hidden layer with multiplied with some matrix vector, weight matrix A, and this F1 is introducing some non-linearity into this AX. So F1 is called as the activation function, and A is called the weight matrix. So this process goes through all the hidden layers, and finally the Y can be calculated as this function. So this okay, so once this weight has been assigned, we need to guide the actually evaluate how the model is trained. So for that, the cost function is there. So which evaluates the accuracy of the prediction Y. And if it is not up to the level, then optimizers what it does to minimize the cost function by updating the weights in each iteration. So the cost function and optimizers, cost function used in our study is the mean absolute error, and the optimizer will be the random optimizer. So talking about the input in our model. So elliptic flow depends upon the pseudo rapidity, mass, PT, and centrality of the collision emitted particles. So elliptic flow can be calculated using event plane fixed. In our study, V2 has been calculated using fixed event plane, that is site R is set to 0. But and so the input will be the since V2 depends upon eta, mass, PT. So we take eta phi space as the primary input space, and we take the weighted PT, mass, centrality as demonstrated in these figures as the weighted as the pixels of the study. So this 32 into 32 weighted is the take X as the input features. So there are 3 different features with 3072 features per event. So there are 32 into 32 into 3. So total will be 3072 features per event. So the data I have been using will be the MPD data, MPD collisional data with center of mass energy 5.02 TeV. Okay, so the design architecture will be as follows. So the input vector has 3072 features, which the input layer takes the 3072 features and converts into 128 nodes. Then this 128 nodes goes through 3 hidden lanes, and finally the output will be predicted. The final layer has signal input. So the optimizer, okay, this ReLU will be the activation function, and this rectified linear unit which converts this X into so X will be if X is positive, the output ReLU of X will be X, and if X is negative, then it will be 0. The cost function used in our study is the mean squared error, and the optimizer is random optimizer. So we have used early stopping mechanism with maximum 10 epochs. If the training is not improving, then the training will be stopped after 10 epochs. And in our study, we have taken maximum epochs will be 60, and the base size is 32. Then we need to see the quality of the training. For that, we have plotted this loss function, the value loss with respect to epoch for training and validation data. We can see that the training for both validation and training is of the order of 10 to the -4, which represents both training, and the difference between validation and training is very low, which represents no under or over 50. In the second plot, we can see we have plotted B2 true versus B2 predicted. As you can see that B2 true equal to B2 predicted state line is highly populated, and this represents good training, good prediction. And we have used several bin sizes as our input, but this 32 plus 32 bin size is better and faster than the others. And this we have tested our model with noise sensitivity. So we have the noise is actually modified, is given as follows. So for each Fij, where j corresponds to feature and I is the ith event, so we have added the noise Xij by W, where W corresponds to weight, which can be several values, and Xij is the is a random number generated between the between the standard deviation of ith feature. So we have taken several weight values, and we can see that the prediction for different weight values, uncorrelated noise is still good. But for W equal to 0.1, the prediction is bad because the noise is too high. Now going to the results. Okay, so we have trained our model with minimum base data, and then we tried to predict our results with centrality. As you can see that, yes, as you can see that the prediction for centrality with MPT and DNN is pretty good, as you can see in this plot. But since MPT is not able to predict the LS data, which can be actually improved by using different settings available in MPT. And we have trained our model with 5.02 GB data, but our results for 2.76 and 200 GB data is still good. This means the energy dependence is also taken care of by our DNN model. Then what we tried is to predict our V2 with different PT bins. So we can see that the prediction for DNN and MPT is still pretty good up to certain PTs, 3 GB, but after that the prediction goes down, maybe due to the lack of data. And we have plotted the delta V2, mean square error of V2 with respect to V2. As you can see that the mean square error of V2 is still within the 10%. So to summarize our study, the elliptic flow has been well predicted, and the centrality and energy and PT dependence of the trend is still retained by the model. So DNN model is quite robust and is less sensitive to the uncorrelated noise. So the outlook of this study will be to test a particular dependence, and we want to implement non-zero reaction plane and randomize it and see how the model reacts for different event plane angle. So this DNN model does not account for the non-flow effects, which we might take in our next study. Thank you.
Thank you, Suraj, very much for the very clear talk. Is there a question from the audience? Because I would have some questions.
Yes.
That's first from the audience.
Okay, thank you for your presentation. I have a question that's about your deep neural network. When you training this model, whether you did some cross-validation for the train set and the test set. Thank you.
Yes. So as you can see that the validation which is new to the machine has been done, and this prediction is quite good.
So that upper curve is about accuracy on the test data set, right? Okay.
Yes. So all these are actually new to the DNN, and these are quite good in prediction.
Okay, thank you very much.
There are questions?
Thank you.
Okay, so maybe I can ask on slide 8, I think you have shown that what is the information that is encoded as color channels, yes?
Okay.
First question is that have you considered somehow that, or have you checked what is the most important information? I mean that what happens, for example, if you if you don't include the mass channel, or what happens if you include one more, a fourth color channel, like the baryon number, for example. And the other question here is that what is the motivation for this green channel? So why do you take the logarithm of the square root of s?
Okay. So to answer the second question, so the energy you can see is very huge. So the order of 5020, 5000. So in order to reduce that, we have introduced a log. So to keep it within some range, so that that there is less deviation in the training. And to answer the first question, actually we have tried, but the results are not actually that up to that level. It is still good, but the variance will be too huge to say.
Okay, thank you.
Thank you.
There is another comment.
Hi, Suraj. This is Gary speaking. Please go to the very last slide. So you mentioned that there's some way to improve the model, and the question is, what do you think how we can improve the model?
Okay, sir. So we haven't thought about. So this is one of the flaws that if you want to actually apply this model to experimental data, so we need to take into this account actually. So otherwise, the event planning will, there is no. So this and so in order to apply for in the experimental data, we actually need to take out the non-filters. If we can do that, it will be better.
Do you think we can calculate higher cumulants?
Actually, so if we can calculate cumulants, but that will not be event by event. So we need to train our data event by event, and the cumulants will not be that effective.
Okay, thank you.
Thanks.
One last question, just for curiosity. The very same network, have you tried with proton-proton events?
No, I haven't tried.
It would be interesting to see what happens.
Yes, actually, yes. So
okay,
we can
you.
see that. Yes. Thank you.
Okay, if there are no more questions, then thank you again, Suraj.
Thank you.
And our next speaker will be Ákos Sudár, who is supposed to be online. Ákos, can you hear us?
Yes, I can hear you. Could you hear me?
Perfect. Yes, yes.
Okay, so then can you see my slides?
Yes, perfect.
Is this control in the wrong space, or is it acceptable?
I think it's fine. Yeah.
Oh, okay. So then I will start.
Go ahead.
So welcome everyone. Today I will speak about the image reconstruction of a proton-computed tomograph, which is a huge linear problem. I would like to, how to say, visit a development process from step to step, which is mainly a plan by now, but I have started this queue to improve the speed of this of the solution of this huge linear problem. As you will see, it requires a lot of improvement because it's very slow in the first implementation, but as you will see that there is a reasonable chance to improve it to for a acceptable time, at least for scientific purpose. Okay, so let's start with the motivation, which is the proton treatment. So proton treatment use the advantage of Bragg peak in the energy deposition curve protons, which can be focused into a tumor. So it can be used in a more advantageous way to radiate tumors than the X-ray machine, than the MEV energy range X-ray machines which are used these days. And yes, thanks to this advantage, the proton facilities the number of proton facilities is rapidly increasing in the world, and this increase the motivation to make this technology more precise and more accurate. And the main goal is to reduce the safety zone around the tumor, which mainly and a reasonable fraction of this safety zone comes from the fact that the relative stopping power cannot be measured enough accurately with a commercial X-ray machine. And the relative stopping power is necessary to calculate the stopping position of the protons. So the Bergen PCT collaboration, in which I am a member, and set a goal to develop a proton computed tomograph, which can overcome this limitation of the relative stopping power accuracy of the commercial X-ray machines. So the group designed a detector concept build of monolithic active pixel sensors developed at CERN and called Alpide, and we set a goal to measure 1 million proton per second within a small area of the detector, which is possible with the use of the advantage of this high granularity, the state-of-art silicon pixel detectors. These are so these detectors, in one hand, these detectors are used to measure the trajectory of the protons behind the patient. On the other hand, these detectors are implemented alternatingly with calorimeter, with energy absorber layers, and this results a calorimeter detector, which is working on the fitting of the Bragg-Peak curve into the energy, into the number of firing pixels in these silicon pixel sensors. And this results a more accurate energy measurement than a calorimeter would result, than the calorimeter would result if we would simply calculate the energy of the proton based on the last silicon pixel detector layer in which we measure the proton. And we our goal to reach better than 1% relative stopping power accuracy. My contribution in this group is to develop and test new image reconstruction algorithms. And the main, I would say, the main model of the image reconstruction algorithm is visible in this slide, which says that the image reconstruction is a huge linear problem. In the right-hand side, this A matrix is a system matrix which defines the interaction between the proton trajectories and the volumetric pixels of the patient called voxels. And it's a huge matrix containing so it's a huge matrix, which makes our problem difficult to calculate. So, and the X vector includes the relative stopping power of the voxels, and the Y vector includes the kind of integral values through the proton trajectories of this relative stopping power, which can be calculated from the energy loss of the protons. And our goal is to reconstruct this X vector, which is our image of the patient. Okay, and it's a huge problem which we have to solve, as the X vector usually is in the order of magnitude of 10 million elements. The Y vector is in the order of the magnitude of 100 million of protons. So the A matrix is huge. So we cannot use how to say, usual solvers for the linear problem like pseudo inversion, but we have to use special algorithms. And yes, I use the Richardson-Lucy algorithm from this algorithm. The main aspect of my work is that the algorithms usually calculate the proton trajectory and the voxel interaction based on the intersection between the voxels and the trajectory itself. And I didn't, but as long as we cannot measure the trajectory or estimate the trajectory itself precise enough, of course, because we cannot measure the proton inside the patient, so we only can give estimations. I don't want to I would like to model the interaction between the voxels and the proton trajectory based on the density distribution of the probability that the proton goes through the given point. So how to say my voxel and proton interaction calculation based on that based on the probability that the proton goes through a given distance from the approximated path of the proton. Okay, so and anyhow, this requires to calculate the interaction between proton trajectory and a huge amount of voxels, based order of magnitudes more than it's the more amount of voxels than used in the literature. So that makes that my problem is even, how to say, my problem is even more difficult to handle from a computational power point of view. So what I have to deal with this problem is for NVIDIA 1080 Ti graphic cards in the GPU laboratory of the Wigner Research Center, and I programmed these graphic cards on CUDA C++ programming language, and I have finished my first version of program code, which can reconstruct this Lorenzo phantom in a reasonably good quality. I reached good spatial resolution and acceptable relative stepping power accuracy. So so how to say, it's visible that the algorithm itself works and can reconstruct the image, but my main problem now is that it's very, very slow. So even to reconstruct this one slice of the phantom takes about 10 hours with the use of 3.6 million protons. And of course, I would like to reconstruct in the reality at least 100 slices, and I have about 100 times more protons. And as the reconstruction time scales linearly with the number of slices and in a linear manner with the number of protons as well, I expect 10,000 times more running time, which is simply not acceptable. Cannot even test. I could not even test this algorithm without optimizations. So my first step is to optimize the memory use. So the first implementation of the algorithm is a kind of dirty implementation. So use the GPU memory in a very inefficient way. What means that I store every data on the GPU memory, and I access them when I need to use them, which is a not correlated memory access, and the results that I access each database more times than would be required. So I started to optimize my program code with the use of shared memory, and my approach now is that I read every data. I read the data that I will use in a given kernel to shared memory, and of course I can do it in a Coruscate SS, and then I need to read every data once to a 3/8 block, not multiply times, and I accept the 10 times speed increase from this development. And now but it would be even too slow. So I need some further improvements. And I would like to show you some improvement calculations that about what kind of, how many times does this reconstruction takes and where are the critical points. Could you see my screen even now?
Yes, but can you please a little bit enlarge it?
Okay, I will try.
Yeah, it's okay.
Okay, so during every iteration, I need to calculate. So I separated every iteration due to memory. Every iteration to two parts: the Hadamard ratio calculation and the updating of the image itself. The Hadamard ratio means that the Hadamard ratio is a ratio which says how good approximation can we give for the energy loss of a given proton based on the actual state of the reconstructed image. And some main points of the calculation is that, okay, I expected 300 million protons, a bit more than 10 million voxels, and I have a memory bandwidth of almost 2 terabytes per second if I summarize the 4 GPU cards. And as long as the problem itself can be very efficiently separated to different GPU cards, it should, this number should be reasonable. And yes, I need to repeat about 300 iterations to reach a reasonable image quality. And okay, here I calculated how many data I need to read the kernel and how many times I need to repeat it. It's not so interesting here. The main interesting, that there are two interesting things here. One is that it takes about 6 hours. So to transfer the data from the GPU memory to the kernels takes about, in cumulative, so during the whole image reconstruction, about 6 hours for the Hadamard ratio calculation, and about 15 hours for the updating of the image, so total about 21 hours, which is a lot. But on the other side, on the other hand, it would be maybe acceptable for scientific purpose. And here the limitation is that the size of the amount of data processed in one kernel is limited, as I have only 64 kilobytes or a bit less than 64 kilobytes shared memory per 3/8 block. So I cannot read more data to the 3/8 blocks. So I have to separate the image reconstruction problem for a lot of 3/8 blocks, which requires, of course, more and more data transfer between the GPU memory and the shared memory. Okay, but anyhow, I started to estimate the computational power, and anyhow, it's clear that the computational power will be the narrow cross section, not the memory transfers. So here I also calculate the same with the same amount of protons and number of iterations, and I assume 45 teraflops per second performance, which is the cumulative performance of the 4 cards. And here the interesting part is how I calculate the interaction between the proton trajectories and the voxels. The proton trajectories itself are approximated by third-order splines, and I have to calculate the distance of the middle of the voxel and the third order spline. And as long as I haven't found any closed expression for this problem, I use an iteration for this. And in each iteration, it requires about 50 floating point operations, and I need 5 iteration to converge, and I need additional 100 flops for calculating the weight itself and for sample work. And in every iteration, I have to repeat this 2 times, once for the Hadamard ratio calculation, once for the updating of the image. So in total, I need to calculate. I need about approximately 700 floating point operation to calculate a voxel and the distance of a voxel and the proton trajectory. And it's it's a big number, but this is only the one problem. The second problem is that I have to repeat it between every proton and voxel, and repeat it in every iteration. So in total, it results about 1 billion teraflop, which is a lot, and it takes about 6,500 hours. Okay, it's not acceptable. It cannot even. I could not even test this algorithm in this way. So I need further optimizations. Here you can see the same calculation, but the same calculation. But I add some extra information to it. So first, what I would like to, what I can optimize is the calculations between the voxels and the trajectory. So as long as the, how to say, the weight, the interaction between the voxels and the trajectories tend to zero quickly if the voxel was reasonably far from the trajectory, which is of course understandable because this interaction coefficient describes the probability that the proton went through the given voxel with the approximated trajectory. And of course, as long as the trajectory is only an approximation, the proton can go through a bit different voxels than the trajectory. But anyhow, if the voxel is far from the approximated trajectory, the chance that the proton goes through that voxel is approximately 0. And if I can calculate, if I can decide with low number of floating point operations to floating point operations which voxel was far from the trajectory, I can save a lot of computational power. So here you can see this 6,500 hour approximation. If I calculate all voxels like it would be close to the trajectory, but if I reduce it to 1% and I say that 99% of the voxels was far from the trajectory, this number reduced to about 250 hours, which is also a lot, but at least could be tested. So it's it's another option to optimize, and I can go further with the optimization of the algorithm itself. And this is based on the fact that it's not necessary to use every data in every iteration. So if I can split the data into 100 smaller packs, smaller sets, and use only one set for every iteration, which is maybe possible. It's out there. In this case, the convergence need to be proved, but based on my previous experiments, it's most likely to be converged. So it has a reasonable chance that I can divide my data to 100 smaller iterations, and some technologies, some solutions like this also available on the literature, but for different uses, so a bit for a bit different algorithm, yeah, so how to in different use cases, which is not trivial that applicable in this use as well, but hopefully yes, then I can reduce this 250 hours to 2.5 hours, which is not the best available in the literature, but at least a reasonable time for testing the algorithm and for scientific purpose.
Akos, please try to
I
approach.
will go back to my slides and I will summarize my presentation. So my presentation was mainly a plan of steps to reduce the time required by the image reconstruction, and the currently working dirty version would requires about 100,000 hours, and now I am developing a version with Koala scale memory access, which reduce this time much, but even a lot. And later I can, and it's simply I would say, so it's a computational step. After I can make a, I would say, implementational a calculation optimization, which reduce this time even a factor of 20. And after I can optimize the algorithm itself, which hopefully results a factor of 100 time reduction. And these are plans, and hopefully in the next GPU day, I can show you the results. Thank you for your attention.
Thank you very much. We are waiting for these very new, nice, faster results. So let's stay tuned. If there are very urgent, very quick questions, if not, maybe we can discuss that later. So thank you very much again. And the last speaker of this afternoon session is Antal Jakovács.
Okay, yeah, I hear myself as well.
Pointer as well.
Thank you.
So you have 20 minutes.
Yeah, thank you. So this talk, I would like to speculate some questions. Mainly the difference about between understanding and learning, or understanding and training. This so the title a little bit misleading, maybe. Representation learning. Representation learning is something like understanding in artificial intelligence. And as I have some motivations and stuff, but before everybody has an experience when someone prepares for an exam, then it is also a good method to make cards, and all of the possible questions are plotted on the one side, and all of the possible answers on the other side, and one can read and one can learn the answers of the possible questions. And that means that one is trained to the exam, and it can be very efficient, actually. But it doesn't necessarily mean that one knows the method, the material which is asked in the exam. But for a written exam, it could be an excellent tool. So what is the difference between the two strategies to go to read the textbook and understand the stuff, and know learn or train by this question card? This is what I would like to go through in this presentation. So the motivation is it's not shared yet. So okay, I
So for motivation, let's look at these two pictures, the two images. And the first one is it's like a noise. So it's nobody. I think nobody can reveal any structure in it. Maybe some shape can be identified. Also, the two are identical as an information content is concerned. So this thing is this Fourier transform and some other transform bay of this cat image. And still, we have a very good understanding of this image, and it's absolutely no cue. We don't know what is the important in this image. It are this little stuff here in this little waves or this shape of in the middle. We don't know what is important here. Why don't we know that? And of course, the answer is clear that the human eye is trained in nature. So we have to process the natural images and not of the Fourier transformed images. And in the natural images, we have some clues how to identify these images. For example, we look for edges, we look for shapes, and so on. We look for textures in it. So we have some clues how to process a natural image. And we have no clue to do this in the Fourier transform case. And actually, it must be true for all of the intelligence, because there is no general learning machine. And just let's check for why it is impossible. Let's go through some arguments. Let's look just for images and times m color images. Let's say let it be 1 megapixel of size, and we can estimate the number of such images. This is 10 to the 7 million. And actually, if we want to identify a shape or a subclass in it, then it can be any subset of the images. Any two images or any n images can be thought to be a class. That means that it is a power set of the number of images, which is 2 to the power of I. So it's about 10 to the 7 million. It's an incredible large number. As opposed, what we have, say, in a computer or in the brain, having some 10 to the 15 information carrier, which means that the representable content of the brain, so to say, is 10 to the 15. It is also very huge and very large number, but much less than all of the possible images. That means that we cannot be prepared to understand, to learn, to classify any set of images. We have to have something before learning, before classification. So for success, we must exploit the specific properties of the observed class before we want to do classification. And for actually the success of the convolutional neural network is based on exactly this understanding of natural images, at least in some way, because we understood that the natural images are usually slowly changing, except for the edges. It contains shapes and textures, and we have if we want to identify an object, it has a translation and scale invariance in it, and exactly the convolutional neural network is based on these ideas. This is why it works for reconstruction of natural images. Okay, so then let's speculate about in general how can this preparation task be done. So this is what I've told you in the introduction. So let's speak about neural network, which usually is a map which maps the input into output and having some parameters. And actually, when we speak about training, then we fix this f function and we try to optimize the alpha in order to have some expected result. So then we have some expectation, an externally given task, which is to be done by the neural network. And that's why training always needs supervision, even though supervision is so mild that we have to reconstruct the same image, for example, in the case of the variational autoencoders, for example. But understanding is something different. Understanding is something different. For understanding, we don't need the function. We just need to consider the input images, only them, and try to understand what is the information content in itself, the input images, the inputs in itself. So that class we want to classify later or learn later some properties of it. What kind of information it consists by itself, by the data. So this understanding, the task of understanding is to find the function class here, the function class here, which is appropriate for a classification task. And this is naturally unsupervised because we just consider the input data, and it is necessarily data driven. And this is kind of a trend in the modern artificial intelligence studies, which is emphasized more and more, this data driven classification, data driven methods. So, and what, as I've said, understanding should precede training, because otherwise we can very much off the topic. So we can if you don't determine well the function class we use, then it can be very wrong results. Okay, just to try to find out the time. Okay, let's go on. Let's have some examples. Okay, so the most elementary task actually is that so we consider the data in itself. No specific action is required. So the only task we want to tell is that an item is element of a set or not. So this is the most simple task we can imagine. Let's look at as a first example, as an example here, two-dimensional the data points in two-dimensional world. In this case, we have just one point, and we then parameterize it as we want. For example, we can parameterize it with the x and y coordinates, and then we can identify this point on the plane. So all representations are equivalent. There is no need to understanding any representation as good as all other. But if we have several points, then it is also a difference. Let's look at these points here. Everybody sees immediately that these points are positioned on a circle. And if we want to represent this data by the xy coordinates, is perfectly good. But these xy coordinates are not independent in this case. Much better representation is the polar coordinate system, when we represent each data by the radius from the origin and the angle, which is a declination angle from the x-axis. And then, but why is good? Why is this representation good? This is good because one coordinate, the radius coordinate, is a constant value for all the data we consider here. And well, maybe it's a big leap, but I draw the general conclusion from this simple example, which can be underlined in mathematical theses and so on, but I don't want to go into detail. Just a statement that, and this is the example for that. In a well-chosen coordinate system, the data coordinates are independent. This is one, but it is a very important thing. And they are either constant. Here, this is the radius, which coordinates we call relevant coordinates or selective coordinates, or lows. These are lows for the data, because for all data, they give the same results. So actually, these are constant over the data set we look, and or so either constant or they are variable. Of course, the opposite of that, which we call irrelevant or descriptive coordinates. And indeed, in this case, the angle makes the distinction between the points without the reference of the other coordinates. So this is actually a one-dimensional subset as we see in it. So the problem in general, to find this coordinate system, and then with this representation, we can do all of the learning stuff very easily. But this must precede all of the learning, of all of the training step. Okay, and it can go so far that we even don't want to or don't need to do any training, at least for simple tasks. Let's see for some examples for that. So if the claim is that if we understand the system well, elementary training is trivial. For example, okay, but some notions, features, I call features the independent coordinates over a set. This is the input, which are either selective or descriptive, so independent over the data set we consider, and either selective or descriptive, either constant or changing variable in the case in the set. Okay, this is not necessary. So classification means that we want to tell that an element X is an element of a class or not. And in this case, we know the laws. And if we have a good understanding, checking all the laws, we'll single out uniquely that this item is an element of a class or not. For example, if I look at a cat, or look an animal, and it has 6 legs, I do not know that it's not a cat because a cat has 4 legs. If it has a horse head, then I know that it is not a cat because a cat has a cat head, and so on and so forth. So for a cat, we have some laws which we look at the cat, and we understand that what makes a cat. And it is very easy to check. But the classification is trivial for us because we have the notions, we have the understanding of what a cat is. For decoding as well, so if one wants to produce a cat, we have to ensure that all of the laws are satisfied, and we can choose the irrelevant, the descriptive coordinates freely, and we must produce a cat image. And also the lossless data compression is a very easy task, because if we know that we want to compress a cat, then we don't need to understand or to store those data, which is true for all cats. We have to just store the differences between two cats. This is a standing cat, this is a tabby cat, and so on and so forth. Okay, so for a good coordinate system, with a good understanding, all of the training and learning stuff is much easier, if not so trivial, as if I said in this transparency. Okay, I just mentioned here that we spent some time thinking about this topic. We have some papers. Let me mention some of them. This is the theoretical basis of where all of this stuff I told you is mathematically formulated and proven a lot of stuff. Then we have used, most of them, we use linear laws, for example, for musical data compression. We have an associated entropy for the understanding, for the representation. I have some transparencies about that. This is a paper when we used laws in the Bitcoin. We revealed laws 5 minutes. We revealed laws in the Bitcoin prices and identified where the laws are changing, which probably means that something have played around with the prices. And some words about reconstruction of mechanical motions, which I think I will skip the entropy part because I have not so much time. I will skip immediately for the reconstruction of mechanical motions in the remaining part, some minutes. So but the idea is the same. I want to use laws. I want to identify laws. Okay. So in mechanical motions, we know that there is some laws behind the motion. So it is it's much easier than in a cat image. But anyhow, so the task is that first we observe the motion. We just have the data. We must use only the data. Know the equations of motion. Discretize the time variable, and we have some d-dimensional motion. And the task is to describe or characterize the motion in a way that we can continue the motion in a plausible way. So continue for t larger than t in a plausible way. Let's see some examples for that. Okay, this is the method we have followed. All of the mechanical motions are locally characterizable with the velocity and the acceleration. Since we have a discrete time, all of the velocity and the acceleration is discrete. The point is that the only thing which we have to look here, we have to take care here, is that in physics, if you have an equation of motion, it must follow for example, it must satisfy energy conservation and must satisfy some constraints. But if you have numerical data, it is not automatically. So we have to identify independently all of the constraints. The energy conservation has to be ensured independently of the equations of motion. This is the one point which we have to take care here. Okay, and now this is the numerical implementation. So we have the motion, the x and the v coordinates, the data are the input. So it's not two-dimensional, it's 2 times n-dimensional, actually, 2 times d-dimensional. Okay. The output is the conserved quantity and the force, and later we use the force to continue the motion. The network we have used is depicted here. It's the extreme learning machine idea, which means that we have one hidden layer and we fix the first weights for random, and we just optimize the second weights. This is theoretically proven that it can work very nicely, and indeed in all cases it's good. There are 2 issues which I want to mention here, just some minutes. The one issue is that very interesting is the issue of chaoticity. So if a motion is integrable, then for a given for 2 initial conditions which are close enough, all of the motions are close enough. But in the chaotic systems, nearby trajectories which start very close to each other will diverge very soon. And that's why there is no method, there is no numerical method that can reproduce a chaotic system. I will show you some examples. So this is one issue which have to understand and which have to know about these systems. The other is randomization. It doesn't matter here. So let's look for the first thing, which is an integrable motion, the gravity pendulum. So pendulum in gravity, so it can stay at the top. Okay, these are the conserved quantities, energy. We see that it's very nicely constant in time, also fluctuating. This is the reconstructed force. The reconstruction is so perfect that you can hardly see the difference. So these are on top of each other. And as a consequence, the reconstructed motion is exactly the motion we have observed. So we have observed the motion until this point somewhere here, where the data, and then we continue with the computed data, and it is perfect. Well, perfect. Yes, computer perfect can be. Okay, let's see the other example, which is my last topic, the double pendulum, which is a chaotic system, a 2-dimensional chaotic motion. And as I've mentioned, no exact method exists that can reproduce the motion for the given initial conditions. And to demonstrate it, I show you 2 examples. We both use the Python Scientific Python package with 2 different methods, but the same initial conditions. And as you see, the first some wiggles are the same, but after that they start to diverge, and then the 2 motions are nothing to do with each other. So we only can compare qualitatively the results, and also that is true for the numerical method, the numerical reconstruction as well. Yeah, you can see here or reconstructed motions. First, the conserved quantities, which were the main point is that these are indeed constant in time, at least in the training period. These are the reconstructed force data. So this is the force. At some points you can see the difference. So actually reconstruction accuracy was 93%, which is not bad. And also it is true that it is finally the numerical, I mean the original data provided by the computer, I mean the numerical solver was not accurate enough, but it's another issue. It's not, but anyhow, the reconstruction is good enough. And here is the reconstructed motion. And the very important thing is that it has conserved quantities, nicely conserved quantities, and it has no runaway solution. If we, in most cases, if somebody tried to do numerical recursions, it has a tendency to have a runaway solutions, and these are very stable for a long time. At so long time we can test it. Okay, so I'm actually done, and let's summarize in some words with my talk. So the most important thing, which I think is a take-home message, is we need an understanding of the data we want to teach. We want to train a numerical, on which we want to train a numerical network. And this understanding is nothing else but to find the best representation of the data. And this means that we need independent features, independent coordinates over the set, over the input, all of the possible inputs on which we want to train. And these must be, if we want to go a step further, either selective or descriptive coordinates. And as an example, we have seen that in mechanical systems, the selective coordinates are the lows, which is true for all of the embedded data. And these are indeed, as I've demonstrated you, these are indeed can be used to reproduce all of the data for a long time period. Thank you for the attention.
Thank you very much for this very interesting talk. Time for questions.
Thank you very much for this nice talk. I became very excited. Have you, first, funny question, have you tried this stock market data?
Stock market data are much, so there is a lot of assets, and you cannot have too many data. Actually, we couldn't get enough data. Mm-hmm. So the problem is that okay, it depends.
So you cannot sweep the whole phase space, which means that you cannot find a good trajectory.
You have to concentrate on a singled out area. Mm-hmm. We have tried the S&P 500, and but not so. More data is needed. Let me tell you that. So okay. We are not rich yet, but we are not ready.
Thank you. Okay, so more physical questions. So in the last two model you presented, mm-hmm. a Hamiltonian system, yeah. Where you have this generalized or whatever coordinates and momenta in your system. Yeah. The question what came to my mind that in this case you somehow set a phase space or a coordinate system, and you have these two variable basically which determines the equations. How about if you forget the coordinate system and just think relatively the points each other? Let me go back to the what you had. So yes. Just thinking on the circle. So let's forget the coordinate system and just think about how relates the points one to another one. It also will plot you a circle and we will recognize as a circle. So in this representation, do you really need a coordinate system, or it doesn't require?
You always have to represent your data. In this case, you can represent it. So you measure. You have some measurements and you have numbers. This is the representation of data.
But if I'm going back, would that mean that you have to set basically a matrix with a perfectly chosen matrix to represent the whole stuff, and then you are ready and you can find the...
I think it's more like that. So anyhow, I don't understand really the matrix stuff here, but anyhow, but always you have some numbers when you have a system. So yeah, you have some data. In our case, in emotion, we have actually an infinite number of data, infinite number 2 times infinite number. So the 2 coordinates, for example. And then you have to somehow figure out that this is not an easy task. It is actually very complicated, and this is the same Grail task. But how to what is the big function class where you want to somehow rotate if you want to speak about the matrices. So what kind of basis do you have to use where the data are best represented? This is a very hard question, and that's why which I didn't show you this is why you may introduce an entropy function for the representation, and you can lower the entropy and optimize the representation more and more. This is not a trivial task. In general, if you can exactly that I've shown you, because of the very large number of possible tasks, this can be solved in general. You have to try. You have to try a function class. You have to identify the coordinates first, and then if you have the coordinates, then you can do all of the training and learning stuff.
I suggest to continue the discussion during the coffee break, because in 10 minutes we have to continue the next session. So thank you again very much.
Ez a Én az előbb hallottam, akkor szerintem jól működik.
So welcome everyone on the last session of today. Our first speaker is Mihály András Pócsai, who will talk about machine learning methods for Schlieren imaging. Please go ahead.
Thank you for the introduction. Today, I am going to talk about how we use machine learning methods to determine the geometrical dimensions of a plasma channel created with a high intensity and short laser pulse in the CERN Awake experiment. So first, I shortly introduce why this is important. In the CERN Awake experiment, the acceleration medium is a plasma made of rubidium because rubidium has a low ionization potential. After the plasma is created, a series of proton microbunches enters the plasma. So more precisely say the SPS proton beam is entering the plasma, and the self-modulation instability is slicing up the SPS proton beam into series of proton microbunches, and the electrons are accelerated on the wake fields, on the plasma waves generated by these set of microbunches. The plasma itself is 10 meters long, and it has a few centimeter diameter. And the task is to measure the diameter of the plasma, the transition region of the plasma at the very end of the plasma channel. And our goal is to develop a machine learning method to evaluate the experimental data. So here I sketch the experimental setup. In the middle of the vacuum chamber, there is a rubidium vapor, and if the vapor is not ionized, then we see basically nothing on this gated camera image. However, if the plasma is created, then using this Schlieren imaging setup, we can detect if the plasma has been created. And the task is by using simple optics to okay, so the forward task is simple. If we know the profile of the plasma, then we can calculate by simple optics what would we see on the detector. These lenses have 75 centimeter focal length. This mask filters out the signal if we don't have any plasma here. And if we have some plasma here, then due to the change of index of refraction, some light is passing through. So this is the Schlieren imaging setup. And for noise filtering purposes, we added up the values along the x direction. And so we have a one-dimensional detector signal. And the task is to so looking at these pictures to determine the plasma parameters from these peaks we see. And this problem is complicated. But as the forward problem is simple, it is easy to adopt it for machine learning methods. So according to physical considerations, we can assume that the plasma has a Gaussian profile. Maybe I show this slide. So the plasma has a Gaussian profile, pure Gaussian if the laser ionizing laser intensity is small, and if the ionizing laser intensity is large enough, then we will have a region where the plasma is fully ionized. This region is parameterized by its diameter because it is circularly symmetric if we consider it in 3 dimensions. Here, the probability of ionization equals to unity. Here, the maximal ionization probability is less than 1. And we can have a length parameter describing this decaying region of the plasma. And assuming, for example, this blue Gaussian plasma profile, we can calculate the corresponding Schlieren signal. It is a highly oscillating signal. It looks like an interference. And we also can calculate the Schlieren signal for a fully ionized plasma channel. Then we have this oscillatory pattern as well, but we have 2 strong peaks here. So what we did is therefore to generate a large set of data with many plasma parameters, and we simulated the corresponding Schlieren signals with additive and multiplicative noises as well. And we trained neural networks to determine the corresponding plasma parameters of the simulated Schlieren signals. So what we did, we use neural networks. I think most of you are familiar with this. We had predicted signal calculated by using an activation function and having this matrix vector multiplication. This W matrix contains the trainable parameters, and this B vector contains non-trainable parameters. A is basically a nonlinear activation function, and between every layers we can use this transformation. So we use machine learning methods or neural networks as non-linear regression. We have multiple layers, therefore we consider this as a deep neural network. We chose the objective function to be the mean absolute error. We tried also other objective functions as well, but these produce the best results. Our neural networks are constructed of dense blocks. It consists a set of fully connected layer with neurons. After the input, after the layer has received the input, a batch normalization is performed, and we choose this scaled exponential linear unit as an activation function, and then we have a dropout value, and in the next layer we have a Q linear activation function. And here is the structure of our neural networks we trained. So we have a set of input data due to the experimental setup. We have 1024 beans. So the input is a vector of 1024 data points. And in general, we have L number of layers with one traditional layer and L-1 feature extraction layers. It is not mandatory to have feature extraction layers as well, but it is mandatory to have, of course, one traditional layer which contains some instances of fully connected dense blocks. In the feature extraction layers, we perform so-called merging. Merging can mean summing the output of the separate layers, subtracting them, averaging them, etc. So there are many functions that could be used for merging. We chose the softmax function for merging, and after these feature extraction layers and the traditional layer, we can insert some hidden layers to improve the results. And then we have some estimations to the 4 parameters of the plasma, naming the maximum of the ionization probability, the diameter, the length of the transition region, and the transverse position of the center of the plasma channel. Here I plotted the 1- and 2-dimensional distribution of the training data. So here you can see a jump. This is what we did intendedly, because in the experiment it is relevant if the diameter of the completely ionized plasma channel is bigger than 50 micrometers. So we included more samples with this kind of with this property. And you can see that these distributions are not uniform. This is because we needed to perform some filtering on our input data with respect to the signal noise ratio. And after filtering out the data, so we have a modified distribution for which we did not have an analytical formula. Therefore, we just plotted it. Our full data set contained around 1.5 million training samples, and we generated a separate set of samples for validation purposes. Here I just saw the 3 best models we applied. We have one, the most simple is, which does not contain feature extraction at all. It is a traditional neural network with no hidden layers, with almost 2 million trainable parameters. We have one model with 1 feature extraction layer, and we have another one with 2 feature extraction layers. This is the most complex one. It has almost 10 million trainable parameters. All of the framework has been implemented in Python using the Keras and TensorFlow backend, and the training and evaluating has been performed in the Wigner Scientific Laboratory infrastructure. And I would like to mention that we have trained for 20,000 epochs. That was sufficient to have good predictions, and we did not see any improvement after 20,000 epochs. So here I plotted the Pearson correlation of the input data. You can see that they are not, the parameters are not clearly uncorrelated from each other. This is due to physical reasons, and here is the Pearson correlations of the models. And we can see, for example, that the Y0 parameter is uncorrelated, which means an already existing translational invariance. The R0 parameter is strongly correlated with the maximal ionization probability. So basically, all these correlations are physical correlations, and we did not apply any constraint in our networks, not even the constraint that the Pmax has to be less than 1 and bigger than 0. The networks recognize by themselves the physical ranges of these parameters. Here I show some correlation plots. The true values versus the predicted values, and you can see that for Y0, for R0, for T0, and for Pmax, all the models have quite accurate predictions, and our most complex model is also capable to predict the maximum ionization probability. For some reason, the other two models overestimate it, but it can see, especially in the regions which is not relevant in the experiment. It is also valuable to have a look at the predicted signals themselves. It is valuable to somehow define the prediction, the quality of the predictions in terms of mean error or mean absolute error. Here is the number of the beans and the average of the absolute error in every beans. We can see that we have the most error where we have the most intense signals. And because I am running out of time, I just very shortly emphasize that we can define the amplitude and phase errors as well for our predictions. And here the blue curves are the relevant. The calculated average phase error is less than 5%. Sorry, it's averagely 5%. And considering the phase error, we can see that it is it is very unlikely that the predicted signals have a relevant amount of phase error. So as you can see on these plots, the most of the predicted signals fit that well the simulated data, as you can see on these pictures. Okay, we have also tested the robustness of our models. So in the parameter ranges where the models have not been trained, this means that we have checked how the quality of prediction changes if we change the corresponding vapor density, and we also checked how the quality of prediction changes if we change the intensity of the probe laser. And our conclusion is that even outside of the trained value of parameters, if the predictions remain valid, if we have only a slight change in the vapor density or probe laser intensity, then we have an acceptable amount of error in the predictions. To be physically more realistic, we plan to investigate and improve our model by taking into account the displacement of the mask in the experiment, variations of the ionizing laser intensity, and also we also try different plasma profiles, because the Gaussian profile has strong physical considerations behind it, but in experiment it is obviously not a perfect Gaussian. Okay, so I would like to say thank you for all of our supporters, and I would like to thank your kind attention.
Thank you very much. Time for a few questions.
So as you have shown, the feature extraction helped a little, so it halved the error. So have you checked what kind of feature did it extract?
I mean, so we have tried summing averaging and softmax functions as feature extractors here, and we only checked how primarily the correlation plots. These were the primary measurements of the calculations, and if we saw improvement, then we accepted that that this is best choice for feature extraction. At least according to my understanding, we did a phenomenological work in this area.
I'm just wondering, how did you decide which network structure you should use? How many network structure? How many hidden layers? Size of each layer? So, is there any strategy?
Yeah. So basically, we tried many structures. I go back to these slides. So I set a boundary that since we have 1024 pins in the vectors, I did not apply any layers which contains more neurons, and I also try to have layers with not too less number of neurons. We had models with final layers containing only 32 neurons as well. So basically, we tried many structures and selected those that gave the best predictions. We also tried applying hidden layers, but we recognized that if we apply hidden layers, at least at similar structures, then we can observe signs of overlearning, overfitting.
So if there are no more questions, then thank you again. And our next speaker will be Zoltán Juhász.
Hallatszik? Okay, thank you very much, and thanks for staying. Okay, so staying with the plasma topic for a while, and what I want to talk about is a collaborative work with the Wigner Research Center, with Peter Hartmann sitting over there, supporting me not to be scared, and with Zoltán Donko. And we started this work a couple of years ago, and we wanted to speed up plasma simulation. This is stepping. Yeah, nothing. Okay. Thank you. So I want to start with a little bit of context if someone's unfamiliar with this kind of plasma and plasma simulation. So basically, for simplicity reasons, I will talk about one-dimensional plasma only, and we have a capacitively coupled or driven plasma system with high frequency signal, and the result is a changing electrical field inside the plasma, which is ionizing. Am I correct? Sort of. Anyway, moving particles. I'm not a physicist, okay, so I'm just changing bits. The interesting part is the ends or the sides of the plasma where electrons are
moving obviously quicker than the heavy ions. So the real problem from a computer science perspective is the simulation time. Typically, they were using about 100,000 particles, electrons and ions, and the CPU execution time was hours at least, but rather days and sometimes weeks or even months. So we wanted to speed this up, and the core of the simulation is not direct interaction, but a particle in cell method, which is basically means we use the field, the electric field, discretized, and the particles move around in the field and deposit their charges on this hypothetical grid, and we solve the Poisson equation to get the new field and then move particles and so on. So it takes runs like that forever, basically. Okay, we also have collision to make a little bit more interesting everything, but I want to talk about more the GPU side. So we developed a single GPU implementation for this. The initial target was 5 to 10x speed up. We got slightly better results than that. So we got enthusiastic, and now we are looking to move to multi-GPU systems. And I'll give reasons why we want to do that. But first, the structure of the code. So this is the generic simulation loop. And basically, in the first version, we just ported each step into a straightforward CUDA kernel. And we were running that for many cycles. And then we optimized this because there were many other problems. But that was, I think I told 2 or 3 years ago, so I won't repeat that. Basically, at the end of the optimization was that the many little kernels were merged into a few larger kernels. So we ended up with 3 kernels in the loop, 1 for electrons, 1 for ions, and 1 for the parallel Poisson solver to move CPU solver onto the GPU. So this is the starting point, and we discovered interesting behavior in the code. And the first was that with the typical particle count that we used, we got about 50x speed up, which was well beyond our target. But the speed up went up as we increased the number of particles, and it sort of plateaued over 1 or 2 million particles. And then we looked at the per particle execution time, or relative execution time in other ways. And that shows also that the particle execution time is decreasing continuously up to about 10 million particles. So that means the GPU is actually increasing its efficiency as we increase the number of particles. So we give more work to the GPU and becomes more efficient. So 100,000 particles is really not enough to gain maximum performance. But if we reach 1 million or 10 million particles and we want to go further, we won't be able to gain more speed up with one single GPU. So let's say if we reach this particle count area or size, and we want a little bit more improvement in execution time, the only option is to use multiple GPUs. And the European Union started this HPC program. Part of this includes the deployment of three exascale computers. One is LUMI, which just started operation. The next one will be Leonardo in Italy, and the third one in Barcelona, probably in 2 years' time. And partly because of this project, but partly because we wanted to do it anyway, we started to look at the multi-GPU implementation, and we promised to create a large multi-GPU program that can be executed on these pre-exascale systems. Okay, so we have weak and strong scaling. Strong scaling would be increasing the number of GPUs to reduce the execution time. Weak scaling is to be able to simulate larger systems without increasing the execution time too much. So that's the goal. And here comes the technical bit. How can we do that? So a single GPU is hard enough. But when we have multiple GPUs, that's even worse. So just for the visually inclined, that's a typical GPU system, one node, 4 GPUs. We can have 8 GPUs, even 16 in some systems, but it's a lot of cores. And if we go further, this is Commodore coming soon. And this is Marconi, the user partition that someone can use to 56 GPUs. And this is Leonardo. So it has more GPUs than an A100 CUDA GPU in cores. So it's about 100 million cores, something like that. Okay, so how can we use such a system efficiently? Well, of course, we don't want to run our 1D simulation on 10,000 GPUs, but if we can run it with 100 or even 10, that would be nice. Okay, so how to program? The problem starts with the wide variety of hardware. Some systems have PCI Express only connection. Some use NVLink inside one node. Some actually use NVLink internode or across nodes. Some use some other InfiniBand or Slingshot, whatever interconnect. And the developer has to take care of all this. And if you don't have, for example, NVLink, but you want to communicate with the GPUs, maybe you can use peer-to-peer access in CUDA, which will run through the PCI Express, which works, but sort of slow. So there are many, many problems. And probably for each system, you have to hand optimize your code. You have to change communication strategies and so on and so on. So it's not a nice thing. So we were looking at strategies, how we can move on. I forgot to stop and check the time. Okay. So we were looking at different strategies, and we have, as a starting point, a single node multi-GPU case, which is sort of simple, but you can program it at least 3 different ways. You can have single thread, multi-thread model, or even with MPI. In the multi-node case, typically people use MPI. In supercomputers, CUDA aware MPI. I'll talk about that in a minute. And there are other things like the NVCL or Nickel and the HMEM as programming models. So I'll go through some of these to highlight potential advantages and disadvantages. So this is a typical multi-GPU bare-bone code. This is the key function. We have to set the GPU that the code will run on. Okay, so the only extension for a typical normal CUDA code is this for loop running through the GPUs, setting the actual device, and then using different memory pointers, because each memory address is bound to that particular GPU. So if you use that address on another GPU, the program will crash. So we have to create arrays to store the different addresses for different GPUs. But that looks simple. Okay, so it's not very difficult. But there's no communication here. So you just run your kernel, it runs, finishes, fine. But what happens when you need to distribute data or communicate with the GPUs during the execution? That's when things become a little bit tricky. And now back to our Plasma simulation. This is the single node multi-GPU version that we created. The very, very simplified version. Basically, we have an X vector, the positions of the particles, and we have a field vector. And the field will determine where the particles move. And the CPU will distribute the data structures. I ignored all the other data structures. And basically, we have data segments for the positions and the same field vector for each GPU. So the idea is that instead of domain decomposition, which would partition the grid and run the same sequential simulation loop for each grid cell, we partition the particles, right? Because we have a very large number of cores, thousands of cores, and the grid is usually less than 1,000 cells. So if we want enough parallelism, we have to look for the particles. So this is one quarter of the particles, second quarter, and so on. And locally, we will update the position of the particles, speed, etc., and do a local charge deposition, and we can solve the Poisson either on the CPU, and then we just gather all the partial density vectors, do a reduction, sum, and solve the system and send back the result to everyone. Or we can locally solve the system in each GPU and then use superposition to create the final field, which should be an auto broadcast to the GPUs, and then we solve the next iteration. So this one is working, and for 4 GPUs we got about 3.8 speed up, which is not too bad. The reason we don't get 4 is, I'll go back to that, this one. So when the GPUs get smaller number of particles, the relative execution time increases. So if we had a straight horizontal line, we would get 4 times speed up, but the efficiency is decreasing. Okay, so this is the one that works. And this is the timeline of the execution. So we can see the 4 different GPU cards and the kernels. This is electron kernel, the ion kernel, and a lot of time wasted because in this particular version, the CPU was executing the Poisson version. But this was just an initial test. So the next phase is the multi-GPU. And I would start with the MPI strategy. So basically, this was a single node multi-GPU version. And now we have to make sure that we have further distribution for the nodes. And in the nodes, we have the previous strategy. So if we use MPI, we would have an MPI scatter type of or kind of step to create partitions. And then each partition would be chopped up into segments and sent to the GPUs for local execution. And again, the field is broadcast to every node and then broadcast to every GPU. And if we use MPI, then of course we have to use the MPI reuse and broadcast in the end when we want to distribute the field, the updated field to each node and to each GPU. And that's a bit tricky. Normal MPI is not very efficient because it can only work with CPU side memory addresses. So most GPU systems would use Q.Aware MPI that can work with GPU pointers, GPU memory addresses. But you still have to copy everything through the PCI Express bus most of the time. And the biggest problem is that you have different stages for computation and communication. So it's very difficult to overlap these things with MPI because the communication is initiated on the CPU side and the computation is run on the GPU. So you have to wait until every kernel finishes and then you can start communicating. And it takes long, you have to wait long for the next iteration. So that's not very good. And there are alternative strategies. I'll just skip this. One is Nickel, which is basically GPU MPI. So it does almost exactly the same as MPI, but on the GPU side, and it has a uniform programming API. It's, as the name says, collective communication library. I don't know whether any of you actually used it. It does reduce, scatter, broadcast, the usual thing. And the big advantage is this part here. It works on anything. And you don't have to worry about how you actually launch the communication routine. You don't have to worry about the transport mechanism. Everything will work, and you have the same programming interface. So that's very, very tempting to use. But the problem is it's still a CPU initiated stuff. So we have GPU kernels, and then we have to wait until they finish so we can start with the GPU communication, because now we can actually communicate. Sorry, I don't want to find you. So we communicate between GPUs this time. So it promises to be more efficient or more effective, but we still have this separation of the steps. So another approach is NB-SHMEM that I will talk about in a minute, but I just want to point out one thing here. And this is the overlap business. The entire QDOP programming model is built on the ability to overlap kernel execution. And the reason why we have so many threads on the GPU during execution is to hide memory latency or other latencies, waiting for instructions to finish or waiting for host communication, whatever. So if we don't have enough threads, we won't have efficient GPU programs. And that's the biggest problem with the MPI stuff, because MPI was designed for as many processes, as many processors or cores we have, right? And you run them and they all run, they all finish, and then you communicate. But when you run a GPU program, you have maybe 6,000 running, but another 100,000 is waiting. Okay, so you don't want to wait 1,000 kernels to finish. You want to start communication as soon as possible. So if we could move this communication into the kernel, we could hide, theoretically, the communication. We would have a continuously running, very efficient GPU program. Okay, so that's the latest development in NVIDIA. It's not a marketing talk, but it seems to be pretty good. This is NB-SHMEM. It's a shared memory programming model for communicating multi-GPU system. Actually, this was designed when the Summit supercomputer was created, when they realized the MPI and NCCL just work, or NCCL won't work just as good. And the current version provides all the collective communication we need, but it also provides this very important GPU-initiated communication. So you can write directly into another GPU's memory area, and you can read. It uses remote DMA. That's the model. You have the private memory space, which is the traditional GPU device memory, and you have a shared called partitioned global address space, which is available for each GPU with a GPU identifier plus symmetric memory address. And the idea here is that if you use this, you don't have to use MPI or anything else. You can just run your kernel, and inside your kernel, you can communicate directly with other GPUs. And if you're lucky, you can hide all this communication. And in some programs, you can actually create very long-running kernels. So in typical simulations, we have an outer loop, and internally we have a kernel, right? Like in ours. But you can run the entire loop in one kernel, because now you don't have to leave the kernel if your program allows that you do everything in one kernel and do communication and synchronization at the same time. Okay, so that's what we want to use. And the bad news is it's not yet done, so I cannot report any success. We have to finish this by the end of the year, so hopefully by the end of the summer we will have a prototype working. So next GPU day topic is booked, I think. And hopefully we will be able to see scalable execution, and really the big goal is to move to 2 dimensions and maybe 3 dimensions, where the number of particles will go up to 100 millions or even billions range. And then we will have potentially 100 million or 1 billion particles. And with that, we could actually use thousands of GPU cards, because we still have millions of particles for each single GPU card. And yeah, just the final addition, it has atomic operations as well. So if we have to update counters or density or these things in simulation, we can do that directly, either locally or with atomic head to remote. Okay, I think I'll skip that, and that's it. Ask questions. Thank you.
Thank you very much. Time for one or two very short questions. Actually, I would have a very quick, very basic question. On the slide where you have shown the performance gain for the different GPUs, can you please go back?
Yeah.
Because maybe it's a simple thing, but there is a small bump for one of the GPUs.
Oh,
just
yes.
Curious that what is the reason? Yeah, for the Tesla P100. Yes. For the P100.
Yes, we were thinking about that. The most likely reason is cache, internal cache of the GPU, but we didn't do any serious testing, but that was our guess. And actually, if we do a memory bandwidth test, there's an even more pronounced peak. So up to 1 megabyte of data size on 1 or 2 cards, we have very, very good bandwidth, and then it drops. So probably it caches a large amount of data, and that's probably the
Okay, thank you.
Can I just say one closing sentence, because I think that's important, and I want to join to the speaker of the Proton CT talk, where he started with a 1,000-hour implementation, and the plan is now to reduce it to 2 hours. So I just want to say to all of you that GPU programming is not about using a GPU. Just having one is not enough. Programming it is the hard stuff. And it's not just writing a program, but knowing what algorithm to use, how to change the algorithm to match the hardware. That's the difficult part for almost all. So you really have to think carefully about that.
I don't think Ákos is online, but I mean, in that project, we are at the stages we're applying an algorithm which was never used for this type of thing. So first we have to find the algorithm, then we can turn to the point what you suggested, absolutely.
Okay, thank you for this very important message. And yeah, a very quick question.
So I have one question. Do you know how many times have you redesigned your application?
How many times did we redesign?
Yes.
I forgot. No, sorry.
Not
I forgot.
exactly.
No, I stopped counting. Peter, the one-dimensional, I think we had at least 10 prototypes, and another 5 optimization. And for the single node, I had at least 3 versions, and for the multi-node MPI, I have the second version, so it's a nightmare.
And do you remember the order of magnitude, the speed up you gained from the first one to the last one?
Yes, I think we have some of those numbers. So we really started with 3, 4, 5x, and then it just improved over the time. Yeah. But for the multi-node, the biggest task was to actually get it working and providing it and making it give good results. It's very easy to mix up all these addresses and pointers, vector partitioning. It's very easy to get lost in the data jungle. But it's good fun. The message is there's a positive one, so do it. It's fun.
Thank you very much. I think we should move on. So thank you again. Our next speaker is Balázs Majoros.
Okay.
You have 20 minutes. I will show you the 5-minute film.
Okay, thank you. So, hello everyone. My name is Balázs Majoros, and I joined Gergely Gábor Barnaföldi and Gábor Bíró around a year ago in the project of the Hygiene++. So I'm going to show you the results of the tuning process of the Hygiene++. We started around a year ago when I joined, and my job was to tune this Monte Carlo event generator to produce a good fit to the experimental data. So try to move. Yeah, it's turned on, but okay. So, quick motivation. So why Monte Carlo event generators are important. So first of all, it provides a very detailed simulation of high energy collisions, and they are widely used in the theory and community to test the standard model and to make predictions and to design new experiments and it's used to analyze the data or to simulate the collisions. So the first part is that it is very computationally expensive. You can see one of the picture here. So this is one of the events, and this is like 1% event collision. And to simulate one event, it's quite big, but we have to do it like millions of times to get good statistic. So to get good statistics, we have to run it for days or weeks, these simulations. So it's quite computationally expensive. So and it's more expensive if we just not colliding protons, but we colliding heavy ions, where we have lots of particles, and you can imagine it by like multiplying this image like 1,000 times. So there are a lot of events going on, and there are lots of things to store and to compute. So this is a very computationally demanding task. So this is where Hygiene++ comes into the picture, because we are trying to tune this. We're trying to build a Monte Carlo event generator for heavy ion collisions, and so the Hygiene stands for Heavy Ion Jet Interaction Generator, and you can imagine like this is a heavy ion collision, and this is like calculated by the Glauber model, and this is a successor of the old Fortran Hygiene. It is rewritten by Gábor in C++, and now it currently supports CPU multithreading. And the hard part is that it is, in order to get a good fit and to produce meaningful output, its output depends on several internal parameters. Like these, for example, we had to examine 40 different physical parameters, and these cannot be computed analytically. We have to simulate every parameter because there is no equations for them to calculate. So this is a relatively easy task if we have like one system. If you're trying to fit one histogram or maybe 10 histograms, this can be a quite easy task. But we had to do it from scratch, and we wanted to give a tune that is working from low energies to LHC high energies, and in all systems, like in proton-proton, proton-atom, and atom-atom collisions. And this is where the challenge lied. And so, give you some perspective, we are simulating in the Wigner data center in high-performing clusters. Yes, and we have 7 nodes, each of them with 16 cores, and each of them with 32 gigabytes of RAM. Totally, we have 5 terabytes of space, but we are not always saving the data. We are using it on the fly and try to analyze them. But in almost a year, this is a rough estimate, but we made around 30,000 Hygiene++ runs, and we generated around 500 terabytes of data in around half a year of CPU time. And you can see that these are the outputs, what we see from these simulations, and the black dots represent the experimental data, and the colorful lines are representing the Hygiene++ outputs. So these are like just some of the histograms, but we have like thousands of histograms that we have to fit to, and this is the most challenging task to like fit every histogram, that we do not make big mistakes in the way. So what we use for the tuning process, we use the Rivet toolkit. This is like this is the histograms that you see. It's just giving us an easy access to plot the results of the Monte Carlo generator, and we are using the Yoda framework, which is just a histogram framework, and we are using the Professor, which is the tuning software that's trying to find the best fit for the experimental data. So, and of course, we use the Hygiene++ for the simulations. So I'm going to introduce you to the tuning process of how we do it. So this is like a circle, and we are doing it like 1,000 times already. So our first stage is always like preparation, talking about what kind of parameters to examine. And after we settle on some of the parameters, we sample this parameter space in a range. For example, like we select 5 parameters that's going to examine. After that, we sample, like maybe make a uniform sample for 100 samples. After that, we are going to simulate all of the samples in the cluster. After that, this is the most computationally demanding task. This like can take weeks to simulate on 7 nodes. So after it is done, we are going to tune. We're trying to find the best fit, and this is where Professor comes in. It's trying to give our the best fit for the experimental data. We can try to sometimes we have to like make decisions to which histograms or which data is the more important to fit to. So we have to be careful what we are tuning to. And Professor, this is the software. The algorithm gives us back an estimation of what is going to be the output. After that, we try to validate the Professor's output. If it's okay and the Professor gave a good output,
we stop and all is done. If not, then we have to repeat this process again. So this is where the time like goes around and around, and this take a very long time to feed the histograms or feed the experimental data well. But finally, we arrived we finally arrived at some of the results. You can see the like around 14 parameters, and these are static parameters, but there are ones that's not static, that you have to make some interpolations if they are not constant in the energy timescale, and after around 100 iterations, this is what we got. So this is still not optimal, but this is very good for now. And with our tune now, the Hijink++, now in all systems and in all energies will provide a very good fit in weak energies and LHC energies. So this is where it is going to be interesting. So I'm going to show you some of the results that we have now. So on the next slide, this is a CMS experiment with a proton-proton collision. And I uploaded the link so you can check the experiment after the talk or something. And this is a proton-proton collision, and this is a measurement of primary charge hadron multiplicity distributions, and it's 0.9 tera-electron volts. And you can see these little dots are the experimental data, and the lines are the Hijink's output. So it fits quite well, and but this is not the Hijink++ main strength. This is going to be the next slide, where Hijink shines is where we have a proton lead or atom-atom collisions. So to give a bit of a perspective, like when two beams collide, they do not always collide they sometimes pass each other. So you can see that if we have two beams and they collide, some of them going to collide and some of them going to just pass over. So this is what I'm trying to show, that if we have a very central collision, then it's marked with red, and if we have a very peripheral collision, it's marked with blue, and this is all of the ranges in between these collisions. So this is a proton-lead collision at 5 tera-electron volts. This is a pi-and-pt spectrum at 7 centrality classes, and you can see that Hijink is very good and precise at these ranges. Maybe at the very peripheral ranges there is not very good correlation, but we are not really caring about that much. But the most central and in between these 6 ranges, the Hijink performing really well. So after this, I'm going to show you, this is a lead-lead collision, and this is a charged particle multiplicity density at pseudo rapidity. So this is in 9 centrality classes. This is exactly like where the last one, where we saw protons and leads, but we just colliding 2 lead beams, and you can see that Hijink is providing very precise results in all of the centralities. And as I said, that's very peripheral collisions. We are not really caring about that, but it's good to have good results there as well. So in all of its system, this is providing very, very promising results. This is more than this is very, 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 very good in that case that no other Monte Carlo generators can produce these results with one tune. So yes, and this is at 2.76 tera-electron-volts, and we are going to move up to almost double the energy, and Hydrogen++ is still scaling up, and we have a very good fit to the experimental data here as well. And this is the same ALICE experiments. The difference is that they measured they split it into the two centralities from peripheral to central, and you can see you can check later the experiments if you want to. So hydrogen is very good at heavy ion collisions. This is what it's meant to do. So in summary, the tuning step of this of the Hydrogen++ is now finished for now, and there are promising results. And currently, we are trying to gather data, and we are trying to publish the results. So the future plans include making the project open source or implement some GPU parallelization to process the speeds up. So stay tuned. Hopefully, you can crush some atoms on your computer too. Thank you.
Thank you very much. Questions?
You mentioned this possible GPU implementation.
Yes.
So what do you think where it should be done, whether it should be most efficient to include?
Well, I'm not quite know the system of the Hydrogen++, so I'm just working on the tuning, but I know I have to consider more for this, so I don't know the answer to that right now. Yeah.
Of the parameterization, how much extent is it? So how much extrapolation is it possible? So how much energy?
Well, not as much. Well, we can extrapolate the data, but it's become that some of the parameters are very sensitive. So like there are ones where you can have wide range, and there are ones where you can have just a tiny bit of difference, and it can cause a lot of mess. So we have to be very careful about the range, and we try not to extrapolate from the parameter set that we got. So I hope we answered your question.
Okay, we are slightly behind the time, so I think we should move on. So thank you again, Balázs. And we arrived to the last speaker of today, Tamás Hegedűs.
Okay, super. Thank you very much. Thanks for staying with me during the last talk. I'm working with proteins, and I'm not a GPU programmer. I'm just a heavy GPU user, but I would like to show you why I need a huge amount of GPUs. We are interested in EBC, ATP binding cassette proteins. Most of them, or some of them, are so-called multi-drug transporters. They are sitting in the cell membrane and using the energy of ATP to recognize and transport a lot of substrate from the cell to outside. Most of them recognize a lot of toxic molecules, protecting the cells. On the other hand, they also influence the systemic distribution of drugs you take. And we would like to understand what is the recognition mechanism and what is the transport mechanism. These transporters contains two large transmembrane domains embedded in the cell membrane and two nucleotide binding domains inside the cell in the cytosol. When they bind ATP, then the two nucleotide binding domains get close to each other, that change the conformation of the transmembrane domains, leading to the export of the substrate. So we use molecular dynamic simulations to understand how the substrate enters to the substrate binding pocket. We use equilibrium simulations, but equilibrium simulation is not sufficient to describe the export process. So we also use accelerated simulations. In this case, we use metadynamic simulations, and for both equilibrium and metadynamic simulation, you need a lot of GPU powers in such a large systems. Last year, we started to study this phenomenon with a plant transporter for various reasons. However, there was no experimental structure for this protein, so we generated a homology model in silico, but it was not stable in MDA simulation, exhibited by the large root mean square deviation from the initial structure. But at the same time, last summer, the so-called AlphaFold protein structure predictor was released. Basically, it solved the structure prediction problem from protein sequence. And the AlphaFold model of this protein was pretty stable in simulations. There was no big difference between our homology model and the AlphaFold model, but it was sufficient to provide a stable protein in our molecular dynamic simulations. And then we also started to work with AlphaFold, since the AlphaFold deep learning method was not tuned for transmembrane proteins. And usually working with transmembrane proteins is very challenging using either experimental or computational methods. Just very briefly, since last fall I explained in details that AlphaFold use multiple protein sequence alignment and protein structure to learn how to predict the structure of a protein from protein sequence. And then you can really input a single sequence to this method based on deep learning, and you get a structure of your protein. And here, an experimental structure and the predicted structure of a transmembrane protein are overlaid, and basically there is no difference. Okay, so the thing is that because of AlphaFold, a huge number of protein structure became available, but you cannot really search them. For example, you cannot go to the database, which contains the experimental structures or the predicted structures, and say that I want to get all the structures of ABC proteins. And therefore, we decided to develop a pipeline to collect the structure of ABC proteins or any specific protein family. And of course, you want to compare them usually. And in the past, you use sequences, and now I think it's time to use structures. You could do this, and because of the basic paradigm in biology,
structural biology that if two protein sequences are similar, they most likely perform the same function and they most likely exhibit the same structure. And today I would like to show you that this paradigm is still stands, but it seems that the structure is more conserved compared to the sequence. This is a very awful figure. You can group proteins based on their sequence. If they are very similar, I mean the sequences, then you can group the proteins into a protein family. It's called PFAM, protein families, and they are represented by boxes. And the similar families can further group together to clans based on similarity. And this PFAM is based on protein sequence. And we were not surprised that if we checked the structural organization of one clan, like the PGP-like, then all the families exhibited the same structural fold. We were somewhat surprised, and we still don't know the reason that proteins belonging to the BPD transporter clan exhibit very different structure. And here you see what does it mean, different structure. The nucleotide binding domain, pink colors, of the ABC transporters are highly conserved, very similar structures, as you see, while the transmembrane domains are very, very different. This is because they have very different functions, and therefore they need a very different module in the membrane domain. And basically, you can use this sequence information from a PFAM family. They are hidden Markov patterns or hidden Markov models, and you can search sequence databases to find a protein of a particular class. However, if you check this MAGB-like protein structure, and you see that the yellow region is one of the match of this PFAM pattern, you see that it is just one portion of the structure. So you cannot really conclude based on this match, sequence match, what is this protein, how the structure like, since this pattern doesn't match the whole structural unit, the protein domain. And for example, if you check a protein from a different structural class, you see the very same structure in one part of the protein, but the other half of the transmembrane domain is completely different. So you should classify it into a different class. Moreover, here you see a ABCG transporter. Here is the nucleotide binding domains, and the nucleotide binding domains contains a very conserved sequence recognized by this regular expression pattern, but there is no match here. Then you start to loosen the pattern to have a match, for example, to set the pattern to have one position which can be mismatched. But then the pattern recognizes this blue region, which shows at this moment that not the sequence is the most conserved, but the structure, since the ATP binds here and not here. So what is the consequence? You have to compare structures. Before AlphaFold, we have at this moment less than 300,000 structures, experimental structures. Now, at this moment, we have approximately 1 million structures from AlphaFold, curated structures, which we really know what is the protein. On the other hand, they plan to release all the structure of all known protein sequences in 1-2 months. So it is 100 million structures. In the last years, for our purpose, we use the TM-align algorithms for aligning and comparing protein structures. And comparing 200 amino acid long proteins took approximately 1 second. But if we wanted to compare 1,500 long amino acid long protein, it took 10 seconds or something like that. And what happens if you want to do pairwise comparison between 10,000 structures, or compare one structure to 100 million structures, or you have protein complexes, or you have multi-domain proteins, then you should perform the structural alignment in all combination of the subunits or the domains. So it's really getting very resource consumptive, and you have to really design how to do this. And I wrote one GPU program inspired by Zoltán Juhász, and that was 2 years ago. And that time we didn't have so many structure. I had problem aligning structure from my molecular dynamics simulations, and that was my first and last CUDA program, I say. But I could accelerate a specific task which took 20 minutes to 9 seconds. I was pretty happy to do that. So we collected the structure. We tried to present it to the wider scientific community on via web application. And what is more important, that the AlphaFold structural database contains only structures for single chain proteins, but we have also multi-chain proteins and very important human disease-causing proteins. So we predicted the structures of some dimers of ABC proteins. Here you see an experimental structure, here the predicted structure, very similar, and the blue colors indicates that the model has high quality, so AlphaFold can predict also these dimers pretty well. And we also expose these novel structures to the so-called 3D Bacon network. Our servers serve as 3D Bacon clients, providing data of our novel structures to the 3D Bacon hub at the European Bioinformatics Institutes. And the users don't know about this, but they use central databases. And the central databases at this moment only the PDB knowledge base, but all the others plans to use this 3D hub in the future. So just summarize that we collect and publish ABC structures, and we try to develop this pipeline in a generalized way for also other protein families. And I think that I can state that here is the age of big data in structural biology. And when you want to search in big data, in that case, it means that you want to compare structures, structural motifs, etc. And for that, you have to either re-implement or develop new structure comparison tools. And this will be most likely very resource consuming. So you need a lot of resource to do that, and most likely it will be, it needs high parallelization, GPUs, etc. Okay, and we try to define the API and data standard for this task in the framework of the 3D Bioinfo Elixir. Mostly I'm in contact with the EBI with Mishi Váradi, and from my lab, most of this work was done by Erzsébet Suhajda. Thank you very much for your attention.
Thank you very much for the interest. Other questions?
You mentioned that the AlphaFold was very accurate in your case. And in general, how in these 300,000 examples, samples, how much?
You know, it's very difficult to say in these cases, since usually if you need a specific protein which is your interest, you go there and you figure out suddenly that that model is not good. On the other hand, let's say very rough numbers. There was most likely there will not be any competition anymore when different methods try to predict the structure from sequence. But let's say the quality of all methods at the last competition was around 0.7, but AlphaFold was above 0.9. It doesn't matter. What does it mean? It's just yes.
I'm just wondering, you said you will have 100 million structures soon, right? And you want to compare in different ways. So the result of the comparison, could that be put into a database so others don't have to do it again? Basically do a collective outsourced version?
Very, very good question, since basically if you could deposit it in a database, then you wouldn't need a high performance method, you just run it once. On the other hand, especially let's say in multi-domain proteins, you don't know which domains do you want to align. And most likely we go to the situation when the user on a web page want to do it in many different ways in a very huge number of proteins, and you just cannot do pre-calculations. Yes.
Thanks. So I don't know about AlphaFold and your MD simulation, what environment they use for the simulation of the protein. But as you are working on membrane proteins, I can imagine that the presence of the membrane and the interaction of the membrane with your protein may change structure and function or whatever, compared to a situation where you have an isolated protein in vacuum. So how is that?
So basically in molecular dynamic simulations, we have a membrane bilayer environment. First, I thought it's a huge problem because it's increased the size of the system, but even if you don't do membrane, it should be water in the case of a similar size of protein, which is soluble. So it's in molecular dynamic simulation, not the membrane, not the number of atoms is the problem, which is caused by the membrane, but we don't really know a lot of physical rules between interactions of lipids and proteins, since it's just very difficult to study them experimentally. On the other hand, what is very interesting with AlphaFold, that in the learning set, AlphaFold didn't have membrane environment, it didn't have, let's say, small molecules in the binding packet, but it somehow in many cases recognized this situation. For example, in our case, in our proteins, there are sometimes disordered regions which are not modeled with AlphaFold at all very well. It's very low quality in the disordered regions. AlphaFold can be used therefore to be as a disorder predictor. But the message is what I wanted to say, that these disordered regions in most of the cases do not cross the transmembrane region. What is very strange, since the membrane bilayer was not there, but you see that the loop goes towards the membrane region, but it stops there and turns back. Of course, if you check a different protein, then it goes through the membrane and it's wrong. But I think this is not the misfunction of AlphaFold, it's just how it is behaves.
I don't see any further.
Thank you very much for the questions.
Thank you for the discussion. Thank you again. And thank you for all of the speakers of today. So that was the last talk for today. Tomorrow we will start again at 9 with the quantum session. So it will be very exciting. So see you tomorrow. Gergely, do you have any further? Have a nice afternoon and evening and see you tomorrow.